Screen third black icon. Okay. Self presentation ఇది ఆఫ్లో ఉంది. చిన్న సార్ ఇది ఆన్ చేయమంటావా? ఇది కూడా లేదు, తర్వాత మార్చాలి.
ప్రెజెంటేషన్ పెట్టాలా?
రెండు ఆన్ ఉంటాయి. తర్వాత ప్రెజెంటేషన్ వైట్ బోర్డ్ తీసేసి
తీసేయాలా? వైట్ బోర్డ్ తీసేయాలా? Very good morning to everyone. It's a pleasure to introduce Dr. Sandeep Anand, a highly accomplished academic and researcher in the field of electrical engineering. He earned both his PhD and BTech degrees from the Indian Institute of Technology, Bombay, graduating in 2013 and 2007 respectively. Currently, Dr. Anand serves as an associate professor in the Department of Electrical Engineering at IIT Bombay, a position he has held since March 2020. Before returning to IIT Bombay, he was an associate professor and from December 2019 to February 2020 and an assistant professor from June 2013 to December 2019 at IIT Kanpur. His international experience includes stints as visiting scholar at Queen's University, Canada and Washington State University, USA. He also brings valuable industry experience from his time at Cosmic Circuits Private Limited and Emerson Network Power. Dr. Anand's research interests are centered around cutting-edge areas of power electronics. He has a keen focus on electric vehicles, wide bandgap devices, and circuits for interfacing alternate sources like solar PV, batteries, and fuel cells. His work also delves into crucial aspects of reliability and power electronic circuits. So I request Dr. Kulkarni sir to welcome Mr. Sandeep Anand with a sapling and a book.
Okay. I hope I'm clearly audible. I have to still use it, right? Because otherwise, वो recording में नहीं जाएगा, right? Otherwise, it's a small room. Okay, so welcome everyone. Good morning. My name is Sandeep Anand. You can see the slides a little bit small here. So I'll zoom in if you require anything more. It's visible, yeah. There are, if you see below my name, there are 4 logos there, right? And I just want to quickly point out what are those 4 logos. So one is, of course, the first one is of IIT Bombay, institute where I work. The second one is the department, electrical engineering department. Third is something called as National Center for Photovoltaic Research and Education, which was established around 2010. It's supported by Ministry of New and Renewable Energy, MNRE, and it focuses on different aspects of solar photovoltaics. Yes, grid integration or power electronics is a part of it, but it has lot more things including solar panel manufacturing, cell research, reliability of solar panels and so on. The fourth logo is of class of 1973 EV Powertrain Lab, which is a lab which we have set up recently at IIT Bombay. And I'll also briefly talk about the lab as we move forward. As the name suggests, this is set up through donation of, this was part of a Golden Jubilee initiative of our 1973 batch, those who graduated in 73. Yeah, I think about me already host has introduced me, but this is sort of what sums up my life, if you see so far. So earlier, 20 years back, I was probably in some similar photo at the back, and then in 20 years I've just moved from there and I've come to a little bit of center focus, right? So if you cannot see me, I don't know, you can now see me, right? So probably earlier I was here and now I'm here. Of course, I was not so happy when I was there at the back. Now I'm happy because these are final exams getting over, right? Yeah, so briefly, yes, I did both my education at IIT Bombay. And when I left IIT Bombay, I joined IIT Kanpur. I was not at all thinking of coming back, right? I mean, I just thought that, okay, I'll go at IIT Kanpur and work. But suddenly, I think I thought of coming back, and then I applied and things went positive. But overall, I think, I've seen both the institutes very closely. Both institutes I really like, I really enjoy. I felt that there is a lot of connection which IIT Bombay builds with its students, and this is what I've felt. I'll give you, I'll show you this example here. So anyways, I think most of the colleges and universities in India are more like, on-campus kind of universities, right? So we have about 13,000 students total at IIT Bombay, out of which about 40% is undergrad, right? So majority, which is 60%, is postgraduates, which includes almost equal masters and PhD students, right? And most of them are residential, but faculty members and also a lot of project staff stays outside. So the overall number of people in campus who come for work is probably a little higher here. But this is the right side one is what I wanted to also point out. So in my first picture, I've shown you, right? So if you see this left side picture, this is Nandan Nilekani main building. Earlier we used to just call it main building. Recently it got renamed to Nandan Nilekani main building. He's our alum, and this is what he tweeted. A special day for me, returned to IIT Bombay 50 years after I first entered the institution. And what I am because of IIT Bombay, I'm confident that this hallowed institute is on its way from being India's best to being one of the world's best. And of course, he has posted this, but more or less, if you talk to any alumni, if you talk to anybody there, it's sort of the thoughts are synchronized, right? So most of the people would feel this way so am I. So yeah, I think it's overall a very positive environment, very positive environment. Anyways, this was again just to, so this was me again meeting Mr. Nandan Nilekani when he came there. So he donated a large amount of sum to our institute, and this was a discussion we had after that. Okay, let's just a few minutes more. So I will not talk about department. Department we have like 65 plus faculty members, and electrical department at IIT Bombay includes devices, control systems, communications, VLSI, power of course, right? But just if I focus on the power electronics and power systems part, so we have about 12 faculty members, roughly 6 to 7 people focusing on power systems, high voltage kind of applications, and another 6 to 7 focusing on power electronics, right? It's more or less equal split. And we have some visiting faculty members who come sometimes. We have some adjunct faculty member as well. About 84, 85 PhD student. This value of course keeps on changing. And master's student batch of 30, 35. Yeah, all the, I mean, I think all the equipments, all the labs, all the softwares are there. These are, you know, some of the labs which are listed down. But if you see, for example, this power electronics lab, we don't have like one lab, we have 10, 15 labs which are all called as power electronics lab. So yeah, a lot of infrastructure, a lot of space, a lot of resources which has been built up, I think over years, and all of those gets used by, you know, almost every faculty member. So so we do like share equipment and very open and easy to work with culture. So I was talking about National Center for Photovoltaic Research and Education, right? So this was set up by MNRE in 2010 as a part of National Solar Mission, and this was the first phase went for 5 years, and then the second phase happened for the next 5 years, and now we are into the third phase, which is for the subsequent 5 years, right? Total funding, I think this is, I'm not sure if it includes third phase, so this probably first and second phase is close to 110 crore, and power electronics is one of them, but thin film group, silicon group, module reliability group, and energy storage group. These are the 5 major groups which are there. And recently we have set up this medium voltage power electronics facility. I think it's been now probably a year or so. So we already had a high voltage lab, by the way, right? And I think typically institutes would have a high voltage lab where, you know, voltages is not the limit, right? You can have 100 kV, 120 kV, whatever you want, but usually those will be very small current. They would just be to maybe, you know, break down an electric field, break down air, or break down some other material or something like that. But here what we wanted to do is have some power electronics facility which can go up to 11 kV for now, and maybe in future we'll try to expand to 33 kV also. So this is how it looks, right? What happens is you have, let me just change the color of my pen. So the 400 volt line comes from here. It goes to the it goes to the circuit breaker, then it goes to the auto transformer, then it goes out. Outside we have a step up transformer which steps it up to 11,000 volts, and then it comes back here to the medium voltage circuit breaker, and this is the medium voltage circuit breaker, and from there it comes out, and then we put our device under test in that facility inside the cage, right? So that's so the idea here is everything gets controlled outside, and we can generate a variable voltage from 3 kV to 11 kV, right? We can set it up based on our requirement, and this is not a very high power. This goes up to 200 kVA, which is okay for us for now because we are sort of making a beginning here, but in future we can easily expand it if we want. We have, you know, probes which can measure up to 20 kV. We have DC sources which can go up to 10 kV, 6 kV also, and, you know, other things. So this is basically a facility where we can test direct power electronics at that level. So we have not just the source, but measuring instruments, DC supplies, all the infrastructure setup, and these are the main topics in which we are working on in this facility as of now. And I'll talk more about these topics as we move forward. So one is PV inverters, right? I'll talk about why there is a need for medium voltage power electronics when we talk about PV inverters. Then we are working on fast EV chargers, electrolyzer. So this was the first thing which we started. Fast EV charger is something which we are starting now. I'll talk more about that. Electrolyzers power supply, there is a clear-cut use case, but for now, because of our bandwidth constraints, we are restricting it. But maybe in future we would also work on that, as well as medium voltage motor drives, right? But as of now, it's number 1 and number 2, which is just starting. Okay, this was the other logo. This corresponded to the other logo which was there in the beginning. So this is class of 1973 EV powertrain lab. Yeah, this is established more than a year back, and the main idea behind setting up of this lab is that we of course have individual labs, right? Like in power electronics, we have a power electronics lab which is used by power electronics faculty. Then mechanical department, they have other mechanical facilities and lab. Chemical, they have their own labs and so on. But this was a place where we can bring together people from different departments, right? So this is not an sort of this. The focus here is that people should be able to come and use it, and this has really helped us. I'll tell you how. But so the structure here, if you see, there is a part of it which is focusing on motor fabrication facility. So we have milling machine, we have wire cut EDM machines, we have winding stations and so on. Yeah, some of these things were conventionally there in mechanical workshops, but those machines coming in front of an electrical engineer, we can sort of figure out a lot of new use cases. So those machines are there. So we are now prototyping our own motors. As of now, we are doing small motors of 1.5 kilowatt, but as we move forward, we can do bigger motors also, right? So right from stamping to wire cutting to fixing everything we can do there. Then we have for power electronics, we have again a few setups which we have created. We have grid emulators and a lot of oscilloscopes and power supplies for us to do research related to motor control, research related to chargers and so on. And then we have a room here dedicated for battery characterization, right? Again, which is not of direct use to electrical engineer, but chemical engineer find it very useful, and that's the reason this lab sort of tries to bring people together. So if you see, as quite a bit of cells gets imported, or OEM rather buys it from another company, so this kind of facility helps them figure out what is the reliability of those cells, what is the life of those cells. They can do modeling, they can do characterization and so on. And then everything comes to middle where we have a dyno where we can just put everything together, do retrofitting, and test the motor plus motor controller, everything together. And then finally a place where we have a lift, so we can retrofit some vehicles there. We have been doing retrofitting earlier by tilting vehicles and those kind of things, but they were not very safe. So now we have a lift and we can properly do retrofitting, and then of course the trial. So this is a small space. Now it's very tight. It's about 1500 square feet. But because of this lab being there now, we have got a big project by ANRF, which is called as E-Rides. And so the idea is now we would expand the space. We will still try to create a common space because the project has electrical engineers, mechanical engineers and so on. So we'll still try to create a bigger common space. That is the idea. Yeah, this is how the lab looks like. As of this was an early photo when there was not much there, but now it's all very cramped and very tightly packed. So we'll probably try to expand. The objective of the lab, as far as IIT Bombay is concerned, was to promote EV research at IIT Bombay by enabling access to these facilities, right? Which it has been doing. Not just internally, but even some of the industries come and use the facilities and so on. Promoting human resource training. So we started a new executive postgraduate diploma in e-mobility, which is like a combination of 6 courses. All courses are online, but they are live. And if a student completes those 6 courses, we award them with an IIT Bombay diploma, which is like an IIT Bombay degree sort of thing. And then a lot of other training programs are going on in point 2, and point 3 is to promote industry academia interaction, and that has also been quite successful. So I was talking about this e-rides project. There we have I think more than 20 different industries coming together and collaborating, right? And some of them like Ather is there, Reliance is there, major component manufacturers for automotive, Hella is there, and a lot of other companies are there. So that's and in that project, it's a multi-institutional project. So IIT Bombay is leading, but then we have a few other institutes as well. We have IIT Kanpur, IIT Delhi, IIT Bhubaneswar, IIT Gandhinagar, and SVNIT Surat as well. Okay, let's come to let's start with the technical part now. All right, so as a power electronics engineer, wherever there is a power processing happening, and the number of power processing that used to happen 50 years back has become much more now. Earlier, if you see majority of the cases, we would directly try to use the original source of energy, right, which is either directly burning kerosene or coal or oil. And now slowly what is happening is most of the things some of the things are still being used, but they first convert to electricity, and then it becomes easier to transfer. It becomes like a uniform energy. It's not that if your engine runs with petrol, it cannot run with diesel. No. So once you convert to electricity, then you can feed to any resources. So therefore, generally, I think globally the trend is that more and more energy is now first gets converted to electricity and then gets used, right? So the power processing in general, electrical power processing has increased over the time. And as a power electronics engineer, one would want to have a very efficient, compact, reliable, and also cost-effective converters, right? If we leave the cost part a little bit aside for now, but certainly efficiency, reliability, and compactness, right? So this is the ideal switch, right, which I've drawn, and you must have seen it in any power electronics textbook as well, right? What do we mean by ideal switch is, there are no losses, switching loss, conduction loss, it switches instantaneously and so on, but reality switches are not ideal, right? So they would have a on-state resistance. What is the on-state resistance? Means if the switch is closed and if the current flows through the switch, then there is an I square R loss, right? So that R is the on-state resistance. One would want that to be either 0 or very low value, right, for your power converter to be very efficient. Then when the switch is doing switching, right, on off, again ideally there would be no loss, but in reality, because it would take a finite time for the current to go 0 and a finite time for the voltage to rise and so on, so there is an IV overlap which causes switching losses, right? So again, we would like if there is low switching losses, right? That way we can have an efficient converter, and not just that, if you have lower switching losses, then you can switch more number of times per second, and what it means is you can increase the efficiency. We can increase the switching frequency, and higher switching frequency leads to smaller size, because the size of the transformer comes down, the size of the capacitor comes down, right? So again, switching loss plays roles in both efficiency as well as compactness. Easy to cool and evacuate heat, right? So this is again a point which I have learned, working more with mechanical engineers, and so if you see the size of the converter, right, we very sort of say that if we increase the frequency, size becomes small, but reality that doesn't happen that way, because if you make the frequency double, the induct transformer becomes smaller, but the losses become double, so you have to have a bigger heat sink, right? So if you have a device which has lower losses plus which has easier to evacuate heat, right, doesn't require a big heat sink, then that can give you a much compact system also. And reliability, right? So robust to unusual situations. If there's a short circuit which happens, it should be able to easily detect and protect it. Over a period of time, it should not degrade. So reliability part, I have few slides toward the end. If time allows, we'll have a look at it. So we want an ideal switch. So far, of course, we don't, in reality, would never have an ideal switch, but this is how the switches have evolved, or rather sort of a brief history of power electronics, right? So all of you are probably have heard about war of currents, right? Between Tesla and Edison, yes. This was close to 1890s and so on, right? So they fought, quote unquote, or rather they competed for which electrical system is better, right? Imagine that time there were no power MOSFET, there were no IGBTs, right? So there is no DC-DC converter, there is no DC-AC converters, right? After that, from 1900s, you had this mercury arc wall, and because of that, people figured out that you can do AC to DC and DC to AC, and therefore people started building high voltage DC transmission, right, using mercury arc walls. So I think the first HVDC was probably in Canada, but nevertheless, so that is something which we started in 1900s, and if you see in 50 years, it appears that more or less in power electronics there was not much happening, but in 1957 or around that point you got thyristors, and that's when really things started changing. Thyristor replaced these big huge mercury arc walls which were made up of glass tubes, right, very easy to break and so on, difficult to transport, so you can have a small thyristor, you can just easily transport, install somewhere. But still thyristor also, the functionality was similar, right? So it could do AC to DC and DC to AC, but that also it could not do in a completely controlled fashion, right? Because you can only turn on a thyristor, you cannot turn off a thyristor. So therefore there was not sort of complete flexibility. You don't have the switch, ideal switch, which we saw in the previous slide. So if you see this region, right, this is the region between 70s and 80s, and of course after 80s is when we had a completely controllable power switch which can be turned on, which can be turned off by applying a gate voltage or a gate current, right? And so yes, people came up with GTOs, power MOSFETs and so on, and this was when you can now theoretically build a DC to DC converter, right? This is when now you can theoretically build a voltage source converter, AC to DC, DC to AC. And this subsequently IGBT was invented, and IGBT became very popular. I have a few slides comparing IGBT with MOSFETs. I'll talk more about that as well. And then I think from 2000s, these wide band gap devices, silicon carbide, GaN, have started picking up, right? And we are moving closer and closer to that ideal switch, right? Because these wide band gap devices have better properties in terms of the conventional silicon one. Okay, let's first see what is MOSFET, what is IGBT, what is the difference, where does this, why are we talking about wide band gap devices, how does it really help us, right? So if you see the structure of a MOSFET, right? If you see the structure of a MOSFET, this is how it would, a vertical MOSFET would look like, right? So it's drain, source, and this is where the gate is, all right? When you apply a positive voltage at the gate, the electrons would get sort of generated here, and which would create a channel, right? This MOSFET is called as N-channel MOSFET because electrons create the channel, right? If holes create the channel, we'll call it a P MOSFET. And this is a vertical structure, so if the current enters from the drain, right, the current goes through the depletion region, which is a big region, you can imagine it, and then goes through this small channel, and then goes through this N and then comes out on the source, right? So this is how a MOSFET would work in the on state, right? If the gate is positive, there is a channel and the current can flow in this way. Of course, current can flow in reverse way also, right? You see the structure, it's all N, 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 right? Even in the P channel you have electrons. So electrons can go from bottom to top, they can also go from top to bottom, and therefore a MOSFET, when it is on, it can conduct in both directions, right? And there is a body diode as well. So if you see, there is a body diode here anyways. But let's focus on the case when this MOSFET is off, right? That means you have removed the gate signal, and now there are no electrons here, right? In that case, and you are still applying a positive voltage at drain with respect to the source, but now there are no electrons there, right? So what will happen is this device will try to block the positive voltage, and while blocking the positive voltage, you have a depletion region which gets generated, right? Since this P region is small region, it is heavily doped and the depletion region extends to only a small length. On the other hand, this N minus region is lightly doped, so the depletion region extends to quite a bit, right? And so now if you see, actually this depletion region is what is blocking this voltage. So if you want to make a 50 volt device, right, you can have a low height of this N minus region, that is sufficient, because it only requires to block 50 volt. If you want to block 1000 volt, then you have to have a large height of N minus. Why? Because it has to block in the negative region, right? Any doubt so far? If there's any doubt, feel free to ask. Huh? So, but now the problem is if you are making a 1000 volt MOSFET, you have a large N minus region, but when this device turns on, the current has to go through this large N minus, right? And therefore there is more resistance. So higher voltage device with the higher blocking capability would have a large resistance when it turns on, right?
I don't know about others, but I did not follow why the gate will generate electrons.
No, gate won't generate electrons. So gate, we would apply a positive voltage here, and the electrons which are, little bit electrons here, maybe very dispersed, they would all come and sort of try to go to that positive voltage. So they would gather there. They would not be generated, they would gather in a very small area, and in that small region the density of the electron becomes quite large. So it becomes like a channel of electrons.
So what you are saying that there is a potential gradient in the bulk semiconductor. Is that what you are saying?
There's a potential gradient between the gate and the P region, or the gate and the source to be more precise.
That's the bulk semiconductor.
I am not sure of the terminology, but I thought bulk would be this, I'm not sure, but anyways, there's a potential difference between gate here and the source which is here.
Yeah. Anything which is not close to the junction is bulk.
Yeah, so this is junction, so that's the reason.
Junction is just junction. So that's
Anyways, I think that's a terminology, let's not get into the terminology
but
part.
yeah, so that is something new for me, that you can have potential gradient in that region. I only know BJT, I don't know this one, so thank you very much.
Sure.
The availability of charges will increase.
Yes,
After applying the voltage.
yes. More charges are there, correct.
So when they come there and then how do they flow?
No, so now if you see, this is anyways N region where there are a lot of electrons. This is also N region, lot of electrons. Only this region was P region where it was sort of, trying to create a barrier. But now if you have a lot of electrons in this region, current can just flow both directions through that small channel. Because there's a lot of electrons there. So that region almost becomes like N in a way, so to speak.
Okay.
Right?
Thanks.
Sure. Okay, so now if you have a 1000 volt device, that would have a much higher on state resistance because of the large N minus region, right, which you have to use if you want to block a 1000 volt device. Okay, so I'll come back, I'll use that point just a little bit later, but this characteristics I think you may be familiar with. Let me just quickly show you what it means. This is basically the drain current, right, or the channel current, and this is the applied drain to source voltage, and these are the different characteristics. Don't look at the saturation region, only look at the ohmic region. So these are basically straight lines which represents a resistance, and that's why we say that when the device is on, MOSFET is on, it represents a resistance, right. Now let's look at IGBT, right, and let's try to understand what is the difference here. Okay, so now this is an IGBT. As I told you, if you have to block a large voltage, you have to have a large N minus region. If you see the previous figure and this figure, the major change you would see is addition of this P region below the N minus region, right? Everything else is more or less the same. So same phenomena. You apply, now names have changed. So instead of source, we are calling it emitter, but that's okay. We can still call it source. We can still call it drain, right? Just for simplicity. So what has predominantly changed other than the names is that we have added a P region in the bottom. How it helps is, that now when you want to block a voltage, right, you want to block a voltage, still a depletion region would be created, right, between this one, the same way, right, and you want to block larger voltage, larger depletion region, same funda. But the positive thing is that when you turn on the device, then some of the minority carriers in this region enters this major region, and they also help in conduction, right, and therefore even though you still have to travel that same length, but understand that there is one more mechanism which kicks in, which helps for faster charge transportation in that region. So therefore, when we want to build a high voltage device, usually we don't use MOSFET, or we don't build MOSFETs, we build IGBTs. Why? Because if we just build MOSFET, it will have a very large resistance. If we build IGBT, that region has an additional component which is technically called as conductive modulation, which essentially means that some holes from P side enters and they help participate in conduction, and therefore resistance comes down.
Sir, can you tell me the three NPN or PNP in this, which are dominant?
What do you mean by which are dominant?
BJT में तीन होते हैं ना, collector, base, emitter.
Correct.
So which are the three? Because there are so many things there.
No, so this is emitter, the top one.
Top one, but
The bottom is collector.
But what is the P or N or what is there?
These are different regions. These are basically different layers which you have grown on a substrate. So if you start with one substrate, you have grown different layers. So these are different layers.
Correct.
Internal. The external is emitter, collector, and the gate. Gate is this region in the middle, and emitter is on the top, and the collector is at the bottom.
Okay. So this is a PNP transistor.
This is an IGBT, which constitutes of multiple PNP, because you see there is NPN, NPP. Oh, sorry, PNP. So this together it's an IGBT which constitutes multiple layers of NNP.
So IGBT is not a BJT.
IGBT is a BJT. It's an extended version, insulated gate bipolar.
That's what I thought.
Correct.
It is a BJT, but it is insulated gate.
Correct.
The difference is that P layer is addition here.
As compared to the MOSFET. Yes. And it helps if you want to build a high voltage device, because it allows minority carrier injection.
It's like a restriction to P layer, not any restriction to flow.
So now that is the point. So exactly what I wanted to talk about. So by adding this P layer, it reduces the resistance of the N minus layer. But the problem is now you will have a PN voltage drop, right? Which is, let's say, 0.7 volt. So therefore, if you see closely, the characteristics of an IGBT is a little bit different from that what I've shown before. It's not a straight line starting from origin. It's not that. There is a voltage drop of 0.7 volt, and then there's a straight line like a resistance. So it's like a series combination of a resistance and a voltage drop of 0.7 volt, right? The resistance part here is much lower. So line is much more steeper than what it would have been, but there is this voltage drop here. Is that okay? So, I mean, it's like a diode characteristics, but you can break it up into two parts. So there is a voltage drop and there's a resistance part, right? Okay, now let me ask this question. If we have to, let's say, make a very low current device, would we build a IGBT or would we build a MOSFET? Very low current. MOSFET? Because why do we build MOSFET? So if current is very small, resistance into I into R will be the total drop. But if you use IGBT, you are stuck with the 0.7 volt anyways, right? Which you may not want to. But if you just have a resistance into I, it will be very small, right? Now if you want to build a very high current device, which one would you choose? IGBT, right? Good, perfect. So now, if you see this, there is a trade-off with current, there is a trade-off with blocking voltage, and therefore in market, if commercially you want to buy a device, you will see that up to 600 volt, you will get MOSFETs, and from 600 volt and onwards, IGBTs become more popular, right? It's not that it's impossible. If you search, you will find 1.5 kV MOSFETs also, right? But their performance would be very poor, and therefore it doesn't make commercial sense, right? So usually up to 600 volt MOSFETs and 600 volt and beyond IGBTs, right? 600 volt, they both coexist, sort of overlap. Okay, and if you have understood this, now there's just a little bit of more of effort and we will all sort of understand what is the role of silicon carbide and how it is changing this whole equation, right? Silicon carbide material has higher breakdown field, right? So you have to apply more voltage to create a breakdown of that. It can sustain up to 3 megavolt per centimeter, right? So you apply 3 megavolt per centimeter. If it's a pure silicon carbide device with no impurity, it can sustain. Silicon only used to sustain 1/10 of it, 0.3 megawatt per centimeter. Now I'm building a MOSFET with, not with silicon carbide, right? Now because it can withstand much higher voltage, I don't require a large N minus region, right? My N minus region can be small because it can block more voltage per centimeter, right? As what silicon could do. So therefore my N minus region can be lesser in height and therefore resistance will be lesser also, right? So if I want to build the same device with silicon carbide, same MOSFET, it will have a lower resistance, right? And that means that silicon carbide MOSFET, that trade-off between IGBT and MOSFET, silicon was happening at 600 volt. In silicon carbide, that trade-off happens at much higher voltage now. Trade-off is still there, right? Still, if you want to build ultra high voltages, you would still want to do IGBTs, not MOSFET. But the trade-off has shifted. And therefore, silicon carbide, you would see popularly, 1.2 kV MOSFETs, 1200 volt MOSFET, 1700 volt MOSFET, 2.2 kV MOSFET, even 3.3 kV MOSFETs, right? Which in silicon you don't have 3.3 kV MOSFETs, right? So that's in a summary how these silicon carbide devices have allowed us to do high frequency power electronics at a medium voltage, right? So that's the basis for why we started doing this work, which was earlier not possible. We could do with IGBT but not with MOSFETs, right?
Resistance line.
Yes.
That is due to which phenomenon?
This one?
Yeah.
This is combination of all the small resistances right from here till this point.
So that is due to material property, not anything to do with semiconductor.
But semiconductor properties, right? I mean, semiconductor is also a material.
So what is the difference between silicon carbide and silicon resistance?
That's what I'm saying. So silicon carbide can block much higher voltage. So you would have to use a lesser length of material to block the same voltage.
But their resistances are similar.
No, conductivity is also better. So it has a higher electron velocity. I'll show that in the next slide. So it has better both ways. It's better both ways. Okay.
What is the disadvantage? Is there any?
Yeah. That's also there. Any more questions on what we discussed? Okay.
What is the
Symbol is different. People draw it in a little different way, but that's okay. I don't mind it. I mean, I don't really look at symbols very seriously, but symbol is different. So silicon MOSFET is same, but GaN HEMT is little different silicon. But silicon MOSFET or silicon carbide MOSFET is same symbol, yeah. But GaN HEMT is a different symbol. But anyways, we are not talking about GaN today, we are only talking about silicon carbide, right? Okay, so now the question is, what about material properties, right? So we saw that it has higher electric field and we saw the advantage of that, right? So only focus on silicon, yellow, and silicon carbide is blue, right? Forget about the GaN. So you can see that the electric field is much higher, right? In one case it's about 0.3, other case we saw it's around 3, right? In addition, there is high thermal conductivity, right? What it means is if your device is switching, I square R losses are happening, switching losses are happening, the heat has to come out, and as the heat comes out, it will create a temperature difference, right? So heat is, if heat flows through a pipe, it's like an electrical circuit, right? So the difference in temperature is same as difference in voltage, and therefore larger heat flows, more is the temperature difference, right? So what ideally we would want, if I want a current to flow through a rod, it should have very high electrical conductivity. Similarly, if I want heat to easily flow through a rod, I want a very high thermal conductivity. And if you see, silicon carbide has much better thermal conductivity than silicon. So it again helps, right? It helps us in easy evacuation of heat. The third thing is the electron velocity, right? So if you see the electron velocity, that means this is the velocity or this is the speed at which electrons can move in that material, which somehow relates to its resistance, right? That also, if you see, the blue one is much more than that of the yellow one. So yeah, so silicon carbide overall, and that's the reason a lot of people think that this is a very promising technology, because it's overall better in terms of these materials. So this one we have already sort of seen. So higher breakdown voltage. So these are the green ones are the material property, orange ones are the phenomena or the effect, and finally the benefits, right? Not going table, but roughly now, as you understand, we can, as you could see, they have lower resistance, right? So lower loss, requires lesser heat sink. Further requires lesser heat sink because they have better thermal conductivity also. Plus, because their size is small, they have smaller capacitances, parasitic capacitances, and therefore they can switch much faster, right? So higher frequency operation is also possible, or lesser switching losses. So this is, in nutshell, how a silicon carbide device compares with the silicon MOSFET. Any questions? Okay. Now this is a question a lot of people ask me, and therefore I just kept a slide there. I will not go into too much of detail, which is silicon carbide versus GaN, right? So it's a picture I've taken it from internet and shows the region where GaN is more popular, where silicon carbide is more popular, right? So silicon carbide and GaN, if you only look at those two things, then silicon carbide is generally better for higher power applications, y-axis is power, and GaN is more suitable for lower power applications, even if you have to switch really faster. Why is that the case? That's more of a device sort of related question, but what I understand by talking to some of my friends who are in this area is that GaN, we saw the vertical structure of MOSFET, right? In GaN, as of now, it's not possible to create the vertical structure. So it's still a lateral device, and lateral device you cannot create for a very high voltages. So that's sort of, and then now why you will ask me why you cannot do that, that I don't have that answer now, but you can look at it. So it's more of a device physics related problem, people who are developing those devices, but as a power electronics engineer, what we understand is GaN is not available for very high voltages, but yes, silicon carbide is there. So whenever we talk about medium voltage power electronics, silicon carbide is what come to your mind. These are some of the companies who make silicon carbide products, right? ST Microelectronics, Wolfspeed, Rome, onsemi, Microchip, Infineon, Mitsubishi, and Semicron, which has recently been acquired by Danfoss. So it's now Semicron Danfoss, right? Power devices are available both as discrete units as well as module, right? Discrete will have only one MOSFET, that's it. A module will have, let's say, a combination of 4 MOSFETs if it's a full bridge, or 2 MOSFETs if it's a half bridge, or 6 MOSFETs if it's a 3-phase voltage source converter. If you look at the discrete devices, the table shows which company is making those devices up to what voltage level. So if you see, for example, ST has portfolio starting from 600 volt going up to 1.7 kV. If you see Infineon, they have discrete devices which goes up to 3.3 kV. And this information I've just picked up from their online, whatever is the available resources. So it's a commonly known thing. Microchip goes from 600 volt to 3.3 kV. Currently we are working with microchip 3.3 kV devices in our lab. Now these are discrete devices, right? If you want to buy modules, which are the pack form factor, then they are very easily available up to 3.3 kV, and a lot of those companies make the modules of 3.3 kV, right? So silicon carbide MOSFET modules are usually available up to 3.3 kV. Now the question is that you see, why are we using discrete and not module, right? I told you modules are generally available, right? Easier to find. Discretes are a little difficult to find. We don't have much choice. Still we are, trying to work with discrete devices there. Can anyone suggest why is that? Of course, there is always any decision you take, there are advantages, there are disadvantages. So there would be disadvantages. So let's not talk about that. But what do you think could be the advantage in using a discrete device and not a module?
Fails only one device.
Yes, if it fails, only one device fails, that's valid. Any more reasons? Customization of design, yes. If you're working with some new topologies or you want to change something, certainly, yes. Anything else? Heat and combination. So combination, yes, we can try new different topologies and all those things. Heat wise, I'm not very sure because module would also have a packaging structure and heat evacuation system. I don't recall exact value, so it's a little difficult to comment. Yeah, they are already you make an edge bridge and you put it in a package. Yeah, or a three-phase VSI, put it in a package, right? So you only have the final terminals coming out. Inside all the chips are there; they are all connected. No, you cannot take out in the module. But there are modules available for that, so you can do that. But yeah, so roughly, I think the advantage is yes. So popular topologies module are available. But the advantage is you can like play around, right? You can do anything. The second advantage is when we talk about silicon carbide devices, they can switch fast, right? Relative to silicon devices because they have smaller parasitic capacitance, they can do switching very, very fast. When they are doing fast switching, the inductance loop of the switching loop becomes very important, right? So what I mean by that is that if this is your DC link capacitors and these are your switches, right? And let's say current is flowing in this direction, right? And coming back in this direction. So when the bottom switch is on, the current flows through this path. When the bottom switch is off and top switch is on, current flows through this second path. Is that okay? Right? This is a half bridge circuit. So either top could be on or bottom could be on. You cannot have both switches on at the same time. It will create a short circuit. If you have bottom on, the current flows through the bottom switch. If the top on, current flows through the capacitor and the other switch. Now physically, if these guys are, they are physically at some distance. So what happens is there is small inductance which exists, which is what we call it as parasitic inductance, right? We don't like it, but still there. So what happens is, now you see there is high di by dt, change in current, which will lead to high voltage across the switch because V equals L di by dt. And if you have these inductances, and if you have large change in current from that path, it would create a very large voltage spike, right? Because in silicon carbide we can switch very fast, so di by dt is even higher. So voltage spike could be even higher. So when we use module, right, you cannot really make them more compact or you cannot really connect them in a more compact fashion. But when you are using discrete, you can actually do much more. And therefore, if you have not seen, go back and try to Google for GaN devices, right? You will see that the GaN devices comes in like very tiny packages, right? And the reason is because you can just connect them in a really closed loop fashion, so you minimize these inductance value, right? So basically, yes, discrete gives you more flexibility in, trying your own design, both in terms of topology and also in terms of the placement or the optimization part. Yeah, but now we have also used discrete for some other application, but for this application for now we are going ahead with discrete, but we have used modules for some other applications as well.
Actually, inductance module is better.
No, module is not better. Actually, the problem is modules was built predominantly for IGBTs, right? Now because as a power electronics designer, I am more familiar with module, so these guys can sell module and I will happily buy. Why? Because it's familiar, na? Oh, dekha hua hai. Okay, let me just buy it. Oh, it has the same footprint. Let me just put it. So that is the reason these guys are making modules. But now, if you see, most of the initial designs, the designs are better with discrete. If you see the Tesla original motor controller, it's with discrete. right? If you open majority of the motor controller now also with discrete. So yeah, so there is some cost dynamics. Modules is effectively cheaper than making discretes, and all those things are there, I think. But for as a designer, discrete gives me much more flexibility. I can try out a lot of things there, right? Correct.
That naturally cancels the EMI.
Correct. Precisely. You can place the devices like top and bottom, cancel the, minimize the inductance loop and so on. Okay. Let me skip this one and let's just see what are the different applications when we talk about medium voltages, right? So most of the consumer electronics, right, mobile phones, laptops, even household, washing machines and dryers and so on, they're usually uses a device of 600 volt, 700 volt. They don't go at very high voltages because in house you usually have single phase. Plus just to make it safer, it's easier to build with lower voltages. Electric vehicles, on the other hand, if you see now, most of the popular cars, MG, Tata, right, they have a battery bus voltage of 500 volt, but that is increasing now, right? So there, as of now, people use, let's say, 600 volt, 700 volt, 750 volt devices, but the trend is the voltage going up. Will it go to 3.3 kV on the vehicle? Maybe no, right? So it's going up, but it will not go to the medium voltage level inside the vehicle, probably, right? The third application, industrial motor drives, yes. So 3.3 kV industrial motor drives are possible. They are already there. If you see traction railways, right, they already have 3.3 kV voltages there, and there's a motor drive, and there are a lot of other auxiliary converters. Renewable integration, right? So, and that's, I think the topic here is also integration of renewables and EV charging infrastructure into the grid. So renewable, there is a lot of scope for higher voltages, right? As of now, if you buy a solar inverter, it gives you output of 230 volt or 400 volt, depending on it's a single phase or three phase. But there is a lot of scope if you can buy an inverter which gives you an output of 11,000 volt, right? I'll talk about that. So is the EV charging. So both these applications, I'll elaborate a little bit as I move forward. But so for now, that's the reason we are focusing on these two. Let me skip some of these, and then maybe if required we will come back and I will show you these things. Let me talk about a basic structure here. Okay, so far any questions? Okay. You have to sort of go, you have to work with my bad handwriting here, partly because that is how it is and partly because this setup is making it that way. No problem, I'll just do it. I think they're recording also, and I also have a record of it. Alright, so this is how a typical solar farm would look like. Right? There are solar panels, which are, some of them are connected in series, all of them few strings in parallel, and they feed to one inverter. Let's call it inverter 1. Okay? Similarly, there are other set of solar panels connected in series and parallel feeding to inverter 2, which is below inverter 1. Inverter 1 produces 400 volt. Inverter 2 also produces 400 volt, right? Few of the inverters will connect together and their voltages will be stepped up from 400 volt to 11 kV, right? If it's even a bigger farm, bigger plant, solar plant, then the 11 kVs would be gathered together and it would be further stepped up to 33 kV or maybe even higher voltages if it's 130 kV or something like that, right? 220 kV maybe, yeah. But typically how this is what happens, at least the solar farms which I have seen. Now in this case, there are two problems. One problem is that you have this chain of transformers, right? And every time power flows through each of the transformers, there are losses happening, right? So each step has a efficiency. Secondly, in night, when there is no solar panel, there is no solar power, right? All these transformers keeps on drawing the no load current or the no load losses. So the transformer loss happens in night also, not just in the day, right? One can theoretically, there is a circuit breaker here. There are a lot of circuit breakers in this scheme which I have not drawn. Theoretically, you can open those circuit breakers, right? And then you can de-energize those transformers at least for night if you don't want to use them. But you don't do it because circuit breakers also have a very limited lifespan. People don't want to switch them every night, right? In fact, people, from my experience, a typical substation manager or a substation caretaker would be really, worried if the circuit breaker gets switched multiple times because their life is limited. They are expensive components, right? Sorry? Yeah, so switching, whenever you do, their life reduces. Therefore, people don't want to switch unless there's a maintenance or you have to have a shutdown of further downstream or something. So summary is that these transformers have no load losses throughout the day, throughout night. The second problem is that these transformers, if you have seen that event that happened in London, near London, which got a lot of electricity out from London, including London's, one of the airport also got blackout, right? The problem was that one of the transformers was under maintenance and the other one sort of blew up, and this is what has happened. So if you have followed some of those things, you would realize that for them to get a new transformer of the same design is not instantaneous. Because it's sort of a custom design for everyone, it takes a lot of time to get a new transformer. It's very expensive, it's built using copper or maybe aluminum, but copper, aluminum plus iron, right? And as such, metals are becoming more and more expensive, right? And which would happen, I mean, it would become expensive because these are mined and these are processed. As the demand is shooting up, everybody wants copper, EV also wants copper. So demand is shooting up, so prices are going up. So transformer prices are also going up, right? So here the problem is, imagine 10 years, 15 years down the line, more cost of those transformers plus these no load losses, right? Circuit breaker might be less than transformer. Maybe, yeah, maybe. I'm not very sure, but maybe. No, that we cannot. I can vouch you for that because I've tried that with one of the companies which I would not name. But we were doing a project and then we tried to convince that look, this is you can do, but they won't. So not just the cost. I think it's also based on a lot of things operate based on experiences, right? And very difficult to make people accept something new that easily. But I think overall. And that would also solve it partially. You still have to install the transformers, still the cost goes in, right? Okay. Let me talk about another problem, which is when we integrate EV into the grid, right? And first let me draw it, then I'll explain it to you. So this is the grid. Okay. So if you want to install a fast charging station, right? You want to install a fast charging station, typically utilities will give you incomer of 11 kV or higher depending on your power requirement, but not below 11 kV, right? So what you would do, you would take that 11 kV, right? You would install a transformer, right? You would install circuit breakers, then you would take that voltage and supply it to charger, which is a power electronic equipment which converts this 400 volt AC into DC voltage depending on how much voltage your car requires, right? So if you are charging a Nexon, let's say it will convert it into 500 volt or close to 500 volt and so on. And that's how a typical fast charging station would be set up, right? There could be one common transformer and then multiple of these chargers, or if it's a very big system, there could be 2 transformers also, right? Now the question here is that in this case, yes, transformer again is a cost, right? It's not only transformer, right? So if you want to install transformer, you have to create a space, you have to maintain a distance from all other equipment, right? You have to put stones to make the flooring. Probably you have to have a protective cage also. So I was talking to some of these charge point operators, right? The people who install and operate these fast charging stations. So they say the cost of this upstream infrastructure, as they call it, is almost same as the cost of the charger, right? So the transformer and everything together cost them the same as the charger, right? Secondly, if you go in any big city, right, Delhi, Bangalore, I mean, you don't have place, Mumbai including, all bigger cities, right? The place is at a premium, right? The land is at a premium. So if you want a big piece of land of your charging station to be occupied by this transformer and other things, you are again losing a lot of money there, right? And therefore, this is sort of the second problem in the conventional way of doing things where we are using a transformer. Efficiency is okay, small problem here, but size and the cost is a major issue, right? And this is how, if we move towards power electronics at higher voltage level, this is how some of the problems can be addressed, not all, some of the problems can be addressed. So imagine you have a solar panel, string of solar panels, right, connected in series and then strings connected in parallel, and they are feeding a power electronic converter which directly gives you an output of 11 kV. So it can be directly connected to the medium voltage grid. I mean, I'm a power electronics engineer, so I call 11 kV medium voltage. I know colleagues in power system may not like that, but for me 11 kV is medium voltage. I get really afraid when I get close to it. So therefore I've written medium voltage, but what I mean is, let's say 11 kV for now. Similarly, you have 11 kV access, you directly have a power electronic converter, and which gives you 500 volt output with which you can charge the vehicle, right? And same way, integration of storage also can happen, right? Because batteries would be 500, 600 volt, and it directly connects to 11 kV using a power electronic converter. So this is the basic, sort of thought process or basic idea why, one should move towards doing more medium voltage power electronics. And now because we have tools to do so, because we have silicon carbide device which can switch faster, which can block higher voltage, so we can, it becomes a reality. Any question?
I have one curiosity.
Please.
Just to tell you that I'm doing master's in EV technology in science regarding this charging stations. And we were talking about power electronics at 11 kV. Now, there are few transmission lines which are DC 5 voltage. There is one big one in Maharashtra. This is in having a background of a special, let us say we lay a special of DC line, 11 kV or whatever talking about. Instead of having that AC and step down transformer, you have from that special grid, that grid will require only 1 or 2 lines. Transmit and what advantage I will and maybe the current towers can take a load of 1 wire extra. And you have, it's a big challenge for EV charging stations to extract power from the grid because the grid is already over. So what is your view on this suggestion? Any level.
To have an extra DC distribution network.
Distribution network only dedicated to EV charging, whereby you step it down from DC to DC and there is no transfer. Another advantage of because there is no frequency, so getting power from any source, you don't need to match the frequency as is needed in the power plants. So there are times these failures are there because of mismatch of frequency. the international powers, if you extract, and the frequencies question is not there, you extract that is it. What are your views?
Okay, so I think what he's saying is, why can't you have a DC distribution system which is exclusively for all the EV charging stations, right? So what are your views? Go ahead. They are not existing, but can we do it? Can we not do it? What are the pros? What are the cons?
Even at Nagpur Metro, you find ESL charging stations.
It's taken from AC. There is no DC.
So what are, anyone wants to say?
DC transmission is costly. That's all. DC transmission is costly. And distance, if we have losses, definitely.
Not have long
So it is not at all economical to have a DC station. Even if we think of getting a supply from the battery stations or the battery operated stations, it would be too costly. So economically, it is not at all feasible. I thought so.
Yeah, so okay, I think, yeah, very close answer is what I also felt, that I don't think technically there is much of a challenge, right? Technically, yes, DC, as there are, lot of literature available, in general also DC distribution system may be more efficient, and but the problem is cost, because AC distribution system is already set up with huge investment over a huge period of time. To do a DC infrastructure or DC distribution system established as a parallel structure with large capability would require a lot of money.
My idea was that existing powers.
But you still require cables, you still require circuit breakers, you still require those things. Yeah, but you do the math, it will not be like 100, 200 rupees, right? What I'm saying is it's probably not a technical problem, it's more of a commercial problem, right? Most of the discoms, I don't know, but I think they operate at a tight budgets and so on, right? I think it's an economics problem, probably not something which we can solve, but a good suggestion, and that is something which is very logical suggestion, because even for distribution network also people have been talking about DC distribution network at homes and so on, but it could not pick up for some reason, but yeah, a very valid suggestion. Okay, so this is how, for example, that power electronic converter which converts panel power into 11 kV grid can look like, right? What does it constitutes of? It has one module where you have panel coming in and you have a high frequency transformer. You still require transformer, right? We cannot go away with transformer, but these are high frequency transformers. That means they are switching at 50 kilohertz. So instead of 50 hertz, they are switching at 1000 times faster. So their size would be, theoretically 1000 times smaller. In reality, it may not be 1000 times, but very, very small size. Transformer provides us isolation, right? So we still require those transformers. And also they give us a large step up, which is not possible using simple boost converter or something, right? So transformer helps us in giving us the large step up, because panel voltage is still low. Panels, you cannot connect the panels in series and go up to 11 kV. You cannot do that. I'll tell you why also. The problem is that each panel has a isolation rating, right? So a panel, 2 terminals with respect to earth can go maximum 1 kV, right? So you cannot connect them in series any numbers you want, right? No. So therefore panel is still, panel string is still limited to 1000 volt, and from there if you want to step up, so you can use high frequency transformer to step up as well as to provide isolation. And all these blocks that you see include silicon carbide devices. Then this is one architecture, of course there could be many more, and here we are using cascaded edge bridge on the left side, and we are connecting multiple such voltages into series to create a 11 kV output voltage. You can think of many more architectures here, but this is roughly what sort of the basic idea is. So there are now two things, as I said, we are working on. One is solar connecting to medium voltage, which is funded by predominantly Ministry of New and Renewable Energy. And the other project is where we are talking about fast EV charging station directly connected to 11 kV, which is recently started, jointly funded by ANRF, which is Anusandhan National Research Foundation, and also GEO BP, which is also contributing into this project. Okay, so let me skip this part. I can give you these slides, so if you want to have a look at it, but let me skip that part. When we want to do this medium voltage power electronics development, right, what are the research problems there? What are the challenges there? Of course, infrastructure is one challenge, right? You need to have the facility to do those testings and operation. But broadly, these are the four, major challenges. First one, let's start with this one, which is the topology, right? You have to figure out a circuit topology. And this is something where I think already, a lot of people in general in India and outside also have been working on, right? Multi-level circuit topologies, DC-DC circuit topologies, integration of multi-level with DC-DC and a lot of those things, right? So that's like forms one part of research which eventually contributes to this bigger vision. The second one is now when you want to use the silicon carbide devices, however nice they are difficult to handle, right? Difficult to work with. We saw one example. If there's more loop inductance, they create problem. They create a lot of other problems also. I can talk about those as well. So designing an effective gate driver circuit for those silicon carbide devices which are operating at a very high voltage, that is the second research problem, right? Or rather the group of problems. The third is the high frequency medium voltage transformer design, right? That is another challenge because conventional transformers would have a sinusoidal voltage. They don't have a large dV by dt across the insulation, right? But the power electronics transformers have square wave voltages and the voltage across the insulation changes very fast. So they have a very large dV by dt which can create a breakdown of the insulation over a period of time. And therefore designing a high frequency transformer at medium voltage is also one of the important challenge.
I have never thought of that, I've never been exposed, but if you put a square wave, what comes out? Does it have square wave or several harmonics?
Of a transformer?
Transformer.
Okay, so that's a good question which I do ask when I take interviews. So I didn't want you to disclose it, but since you are, yeah. So if it's an ideal transformer, right, E Faraday's law is equals to N d phi by dt, right? So if you feed voltage as E, you will get a flux. So if it's a square wave voltage, the flux would be integration of it, which is a triangle.
Yes.
And on the secondary side, again, if you do the reverse, the triangle would lead you to a square wave voltage, right? So ideally, square wave in, square wave out. Practically, square wave may saturate the transformer, right? And in that case, it would start drawing larger input current, which are harmonics current, which would create drop because of the cables and line impedances, which would change the shape of the output voltage, right? So in reality, it would not be perfect square, yeah, but somewhere in between. But you would, if it's saturating, if it's not saturating, then it would be square. Okay, coming back. So this was transformer design. The fourth problem which we see here, and when I say these problems in our labs, so this is a collaborative effort. 5-6 faculty members together are working on it, not just me. And we have, our students working on it. So different people are working on different aspects. So people working on transformer design, people working on gate driver and so on. The fourth aspect is the control aspect, right? Now you have multiple, if it's a cascaded edge bridge, you have multiple such inverters connected in series, right? And on the DC side, you have multiple panels. Some panel may be giving more power, some may be giving less power, but they're all connected in series on the AC side. So how do you coordinate among different inverters without a dedicated communication line, or with a communication line with minimal data exchange? So there are a lot of control related, application of control to power electronics related problems which are also there. The fifth problem, or the fifth, bulk of problem is, and I can elaborate on them, but before I move forward, let me tell you the fifth bulk of problem is reliability of these silicon carbide devices, right? These are new devices. Their manufacturing process is also new. What I mean by that is, I know buck converter, right? Since undergraduate days. All of us knew buck converter from undergraduate days. But whenever we make the buck converter for the first time, it doesn't work, right? And over the period of time, you learn problems. Maybe soldering is not correct, how to actually design the transformer. So a lot of practical learnings happen, and then we know, okay, now we can make a buck converter confidently, right? Same way, silicon carbide is a relatively newer technology. So how to manufacture those devices? On paper, it's perfectly fine, it's far superior than silicon, no questions asked. But how to actually manufacture those devices, that process is still evolving, I would say, right? So people are able to manufacture commercially devices, but they are not as reliable or they are not as defect free as that of a silicon device. So that is one bigger challenge, and therefore there is a lot of reliability related work which needs to be done for these medium voltage silicon carbide devices, right? So 5 broad problems, I would say. Let me talk, I'll try to give, I don't know how much time I have. Okay, so I'll try to give you, a glimpse of some of these problems that we are working on. Okay. Okay, before I sort of begin, just to sort of understand, have you heard of a term called Miller turn-on? Have you heard this term called Miller turn-on? Okay. If this is the node, right, and your top switch is off, right, and bottom switch is also off, that means you are in the dead band region, right, where both switches are off. Now you turn on the top switch, right, you are turning on the top switch. So this node, let me call it alpha potential when both devices were off was something. Let's say if the current was going out, the bottom diode was freewheeling, right? So when both devices were off, potential of alpha was 0. Now when the top device is turning on, the potential of alpha will go from 0 to VDC, right? And this happens faster in silicon carbide than in silicon. So what it means is we can call it dV by dt, and this is what the phrase dV by dt means, that the voltage at the node is changing dV very fast, so dV by dt, right? If your dV by dt is large, it induces a current in this channel. This is a capacitor, right? These are parasitic capacitance of the device. So the current induced is equals to C dV by dt. So a large dV by dt can lead to large current. This large current can charge the bottom gate and can accidentally turn on the bottom device. So you are turning on the top device, bottom device automatically turns on, and this is called as Miller turn on, and creates a short circuit, and your both devices blows away, right? So this is one common challenge which is there, and there you would find a lot of literature, a lot of solutions people have proposed and so on this problem. Yeah, these are like parasitic capacitance getting charged, and then that voltage can turn on the gate. Why it's happening here? It's not that this is a new problem, like it used to happen in silicon also, but silicon, two things. Now one is that it would have larger capacitance values of the gate to source, so therefore it required more current to increase its voltage. Secondly, the dV by dt was not as high as now, so therefore it was there in silicon also. It's not that it's completely new, but it was not as prominent as it becomes in silicon carbide case. So this was one challenge when we do gate driver design, right? Gate driver was one of the problems. This is one of the challenge when we do gate driver design. Let me pick one challenge on let me take one example from reliability also. Okay, let's take this one. Let's talk about, this is also not reliability essentially, but let's look at this one. So in power electronics, although we always try to make sure there is no overlap of the two switches turning on, we always create a dead band and we want to, one switch to turn off, then another one to turn on. But in reality, there is a short circuit which happens once in a while. And therefore, we have a protection circuit which can detect and avoid that short circuit of the two devices. So if you have a half bridge structure like this, right, top and bottom, then both devices, we don't want them to turn on together, that will short the DC link, but it does happen, and therefore we have a protection circuit. The problem is the protection circuit is finally some RLC elements, right, which takes some time to detect if there is a short circuit and then open it. It cannot detect before it happens, right? So the short circuit happens, then the circuit detects it, and circuits open the devices. There is some amount of time which goes in this phenomenon, which was acceptable to silicon IGBT, but that time is not acceptable for silicon carbide devices. So if you really use the same protection circuits which you have used for silicon devices, circuit will be there, no problem, right? And you can say, oh no, same circuit we have put, nothing is happening. But when short circuit happen, that will not be able to protect the device. Why silicon carbide has shorter withstand capability or shorter withstand time? There are reasons, because it has much higher saturation current. These are little more reasons which we need more time to understand. So, but I'll just list down now. I want to go back and read. They have, so silicon carbide devices a much higher saturation current, and therefore whenever short circuit happens, the current goes up very, very fast, right? And that creates a problem. The second problem is the silicon carbide, the chip itself is smaller as compared to silicon chip. And therefore the heat storing capacity is very small, right? If there's a drop of water versus a bucket of water, if you give a certain amount of heat to the drop of the water, it will evaporate immediately. If you give the same amount of heat to the bucket of the water, nothing will happen, right? It will take 1 hour or something for it to get, start evaporating. So the mass plays a role. So because these silicon carbide chips are small, even if the same heat get dissipated, they get fried up very, very fast as compared to the bigger silicon chips. So that's the second problem, right? So yeah, there are a lot of problems. There are so many problems. I had one slide on each of the problem. I'll skip now, but I'll give you the slides. You can read it. And it's only for, within you can use these slides, no problem. Skip. Okay, this is one slide which I want to briefly talk about. So there is a training program which we are conducting at IIT Bombay under National Center for Photovoltaic Research and Education, which I just talked about. And all of us are from IIT Bombay, and 5 of us are instructors for this short-term program. So Professor B.G. Fernandez, and all of us are, by the way, also involved in this medium voltage activity. So Professor B.G. Fernandez, Shiladri Chakrabarti, that's me, and then Professor Kishore Chatterjee and Professor Anil Kulkarni. So we are together sort of created this program. And this is an in-person program which happens during 17 to 19 July. I think the last date is in just a few days. If you want to apply, you can do that. Anyways, I've given a link here, I've given a QR code here also. You can, if you want to register, feel free to do that. And I think with that, I would stop. But if there are more questions, we have some time, I can answer. I don't have any problem. Any questions? I think, any more questions? Sir, I think I have answered your questions, right? You asked something in between. I said I'll come back to it later. I hope.
If others don't have, I will have some. Let others get in.
Sure. No questions? None of the students have asked any questions. How many of you are students?
Ladies scholars, kids scholars.
Oh, a lot of students. Huh? So, should ask some question? Only one student asked a question. Yes.
Sir, at the charging station, can that method of charging can affect the range of that car?
You mean range or lifetime of the battery?
In both the perspectives,
Yeah.
range as well as battery.
Yeah, it can affect both. It can affect both. So, life, of course, because let's say you are pushing more current, then there are a lot of chemical reactions which happen inside the battery, right? There's something called as dendrite formation and whatnot, which I'm not very, it's more of a chemical engineering thing. But so if you abruptly keep charging with large current and so on, it would damage or quote unquote create extra reactions in the battery, which reduces its overall lifetime. In terms of charging it at one go, you may charge it inefficiently. For example, if you are injecting a lot of harmonics, the battery may get heated up. and therefore it may not get fully charged as it would have been a nominal temperature. So both ways it can affect. Yeah. But now how it happens is that usually who makes the battery pack, right? There's a BMS in that. So BMS knows the battery, right? So if I'm making my battery pack, I have my own BMS, so I know what current voltages it can take. So I will tell the same thing to charger, and charger ideally should just follow what I'm asking them to do, and therefore there's a communication between the two units, right? So therefore that problem is theoretically there, but in reality it may not be as prominent as we think, because BMS is telling the charger what to supply. Charger is not thinking itself.
What about range of the car?
Range, if you don't fully charge it, I think that will affect. So if you don't fully charge it for whatever reason, maybe you are injecting a lot of harmonics, maybe you stop charging it before it actually ends up, then it may affect the range. But I think it's more of a reliability problem.
What are the standards for the power density, compactness? You said the compactness is the main factor. So what power density we require for EVs now? Some standards.
Okay, so there are no standards. I mean, standards basically means what? Standard means that you have to meet this if you want to launch your product, or if your product should be, used by people. So there is nothing like standard, but you can do what in industry people call it as benchmarking. Benchmarking means you go online, you try to find 5 products, see what is the power density of 5 products, and you get an idea that, okay, if I do 20% better than this, then I'm proposing something better. So you can do benchmarking. There are, which you can of course Google, and there's no single value, because what happens is different power level, right? The power densities would change, different application power density would change. So if an inverter, the power density, and a onboard charger power density would be completely different, right? I'll tell you few resources. So there is one paper on, if you are interested in inverter or motor controller density, then there's one paper by Professor Ali Imadi which you can look at, where he has done this benchmarking thing of different manufacturers, commercially available inverters, and what is the power density, and what are the target power densities set up by, I think, some of the US organizations. These are not standards, right? Standard means you have to meet. You don't have to meet them. But these are more like projections or future projections, right? The other is this thing happened, Google Little Box Challenge happened, I think, quite a few years back. There again, people talked about power density, so you can get some information there also. Yeah.
Sir, for heat, for thermal management, we are using switches. So if we go for surface mounted, so in that, sir, I don't know how they are managing the thermal. Means in whole through we go through with heat sink, but in surface mounted, if we go for compactness, because surface mounted at lower device. So in that heat management, sir, if you tell something.
Oh, very good question. So, look, you do surface mounting of the devices not because there is better heat management there. You do it because there's smaller inductance loop, right, which Professor Keshri was talking about, right? So, if you can do surface mounting, then the loop becomes smaller. Heat evacuation becomes more challenging, because as you said, now heat will first go to the PCB, and from PCB you have to bring it to the heat sink by connecting some things to the heat sink. So heat evacuation is much simpler if you have a TO247 package where you have, directly connect the heat sink to the device. But there, because you see TO247 has these leads, and the current flows through the leads, and the loop becomes bigger. So yeah, in one way you get better heat evacuation, but you get bigger loops. The other way you get one. So
That is only my question. If we go for surface mounted for compactness and higher power density, how can we tackle this?
it depends, right? How much is your loss? It all depends on that. For example, if it's very, very small loss, you may not require a heat sink at all. So depends on how much is your loss, what is the exact design. There cannot be a general statement that A is better than B. So you design, maybe, I mean, if you would have hypothetically been my student, I would have said that you design with both. You do design A, you design B, you compare. Right? You can design everything, right? On pen paper, I'm not saying physically. Pen paper, you do both design, and then you compare.
One more question. If we go for control side, then we generally got higher energy storage element. So higher order will come. So to make that transfer function,
That is little off the topic, so I can answer offline, right? If that's okay, because audience may not really be able to connect to that. We can talk after the lecture, no problem.
So when we are saying fast charging, what is the time frame that is considered?
Yeah, I think that definition is, of course, now UID has come and now it's like 5 minutes is the definition, but earlier it used to be 1 hour. So I think that's more of a term loosely used to represent you are doing 1C or higher charging. 1C means you charge in 1 hour or faster. So I think that's typically how people would use it. So if you're charging 80% of the battery in 30 minutes, you call it fast charging. Now people are talking about 5 minutes, they started calling it ultra fast charging. So, but yeah, roughly that's the range, but it's not very well defined. So these terms get. So the medium voltage thing is wired, right? Because a lot of power, you want to charge really fast. But then there are some wireless charging solutions on which my colleague Shiladri is working on, which are generally low power, right? So those are not very ultra fast or fast charging because to absorb so much of power, you require a larger surface and so on, right?
And what issues with this, when we increase the number of charging stations, what effect it will have on the grid, since we are talking of medium voltage?
So on the grid, we did some basic calculations, right? So power, energy itself is not a big challenge. The challenge comes more of, let's say, if a distribution system is already overloaded or operating to the capacity, and now evening already it's at a higher load, then evening you charge your EV also. So it's more of a power problem. Energy wise, it's not a big problem, right? So as a grid, we have a lot of energy. So energy wise, not a big challenge. Of course, you still need to grow, but it's more of a challenge where the infrastructure is sort of restricted. And then you may have to upgrade if the number of EVs per distribution system becomes more than a threshold. As of now, I think there is no problem at all, given the penetrations we have. But maybe in future, if the EV picks up, that infrastructure problem may come. But if you see, there are countries which have 50-60% of EVs penetration, like Denmark and all, right? And they are doing. And same thing, you remember, was 20 years back, people were talking about for solar also, right? Nothing happened. We have huge solar, and solar is growing, and other countries it's there. So yeah, there could be some problem in future, but I don't think as of now it's like an immediate problem in terms of infrastructure for the distribution system. I don't think so, because now all these converters are unity power factor, current controlled. You can inject reactive power, you can absorb reactive power, you can operate at unity power factor. Earlier there used to be thyristors and so on, so more of a power quality issues, right? I don't think now it will be too much, but maybe.
And are we really thinking of V2 grid?
Yeah, that people are doing. I think there are now commercial products also. There are cars which can do V2G, G2V. So that is happening, that is there, yes. Any last question? Yes.
How will the charging rate or the speed of charging be affected? We are using the ES.
So it's a complicated question to answer. And I'll tell you why. So try to read. So you Google this question, right? You will find a lot of, because I have tried it. So you'll find a lot of reports which say that, if you try to charge faster, your life reduces. But at the same time, you would read a lot of reports by OEM, by the car manufacturers, who would say, no, fast charging is not a problem.
That's why I'm confused.
Yeah, so you have to, I think I can connect you to my good friend in chemical engineering. This is probably a chemical engineering question. So if you have a friend in chemical engineering, ask them. I have asked my colleague in chemical engineering, my friend. And he also doesn't have a very clear answer to that question, because a lot of factors are there. Now, if you're charging fast, temperature goes up. That might help if you are in a cold country. That might not help if already temperature is high. Again, charging faster, there may be more reactions happening, which may be good sometimes, because faster current can break down some deposit of some material. But it may be bad, because that may lead to some additional charging. So I don't think there is like digital answer to this question.
Fast charging, the faster chemical reaction will increase the internal resistance. So you must drop the life of battery.
But at the same time, if you have, let's say, some extra deposit happening over the electrode, and if you push in large current, that might break that thing and you might get more electrode exposed area. So it can happen either way, na? Or rather both will happen. It just depends which will be more prominent in which condition. Let's not go in that road, by the way. Huh? Okay. Thank you so much. We can chat now.
It's very excellent lecture by Professor Sandeep. He has started his journey at 3 o'clock in the midnight. So very energetic, and he has started the switch and what is the common problem. Also he has shown various facilities in IIT Bombay that he is working and dealing with all the projects and all. It's very wonderful, sir, for coming here, and thank you for this wonderful talk. Take over. You have to take over.
Thank you so much. I think really appreciate Professor Lokande. Of course, I know him from quite some time, and very nice to have Professor Kulkarni as a host, and good to meet other colleagues also here. And very nice to interact with you. If you have any more questions, I'm here for another 1-2 hours. Happy to interact. Thank you so much.
Thank you so much, sir, for delivering the valuable lecture. Now I request Dr. M.M. Lokande, sir, to present the shield and certificate to Professor Anand, sir.
If you have already not done, it is not done, sir. So let's do it anyways. Yeah, please come here. Put some slide here. Stand here. Sandeep. No, you should be front.
मैडम आप यहाँ आ जाइए आ जाइए आ जाइए
Both of you come.
आप आइए चलो ठीक है
One more photograph. आप आनंद सर से मिल
already joined your course, sir, for IT Bombay. Oh, you're coming there? So, and my friends also want to join. So, is there any topic on AI?
No.
Advanced for
I don't want AI. There is nothing on AI there. But if you want to learn more about call accounts, you can go.
So, my project is a leakage current mitigation.
Oh, yeah. So next, what can you do?
Look on sir. I was following your lectures, NPTEL.
NPTEL तो नहीं है. I have few on YouTube, but not
Yeah,
nothing
YouTube
on
like this.
So Ragnar admin.
Sir.
identity was the three-layer added in the last. So, like I also heard that like IGBT was used for low frequency and MOSFET.
हाँ वो मैं बताना भूल गया. तो if you add p layer, then those minority carrier वो n में घुस जाता है during the time of conduction. That is what is called conductive modulation. उससे क्या है वो उधर minority carrier पे रहता है तो fast जाता है current. हाँ then come this side. तो लेकिन but now the problem is when you turn off this device, the minority carrier जो है that takes some time to go away, which causes a tail current when you turn off the IGBT, and that reduces the resistance. Therefore, switching speed of the IGBT to the second data. That has been said.
Sir, please come for copy. Here also you can talk. Sir, actually,
ఏం అడుగుతున్నారు? యూట్యూబ్లో ఏమొస్తుంది చూడు. బ్లాక్ స్క్రీన్ వస్తుంది. పట్టుకెళ్ళు. ఆయన క్యాబ్ ఛార్జెస్ ఏమైనా కనుక్కో, అవి ఇక్కడ రాయి. తర్వాత వెనకాల ఒక సంతకం చేయించాలి, సిగ్నేచర్ ఆఫ్ క్లైమెంట్. డీటెయిల్స్ ఫిల్ చేయాలి. ఇక్కడ సైన్ అవసరం లేదనుకుంటా. ఏమన్నా అయితే అన్ని ఫిల్ చేయించుకొని తీసుకోవచ్చు. ఇంకోటి ఒక్క నిమిషం, ఇంకో ఫైల్ ఇంకోటి.
मकान जी से पूछो। I have sent you.
Yeah, fine. So first we will have black start, yeah. Then दोनों खोल दो तो PDF पे दोनों. हाँ.
ఈ రెండు ఫ్యాన్లు అటుపక్క ఉంది ఇవి ఉంది. While you want to show the slides, please let me know. I
Okay.
will show the slides.
Okay.
If not, it will be in whiteboard.
Okay. Start, okay. So let's start. Yesterday we started with dynamic programming. And if you look at, no matter which method you look at, they all have dynamic programming at their heart, right? And coupled with dynamic, so dynamic programming is an idea, right?
Dynamic programming is an idea. So what it says is, if this is the destination, no matter how you arrive there, and if this is the optimal path to the definition, it does not matter how you arrive there, this is already given to you. So all you have to do is from here, so the optimal is, so if you've got many states from which the optimal path is given, so you have to only, if you are here, you have to only work out this plus this. So you don't have to work out optimal path following that, because that's already decided. Now, to make this clear to us, we got involved with a process, and I want to recall it. What was the process we got involved? Yesterday we made a table. So what can you tell about the table? What is it that you remember about the table? So the table is very, very important. I cannot so this was something like the table we had. So what in each cell, what did we put? Very good. Cost to go, and somebody said action. Cost to go and action. Very good. So cost to go, everybody clear about that? We had cost to go and action. Now in cost to go, what are the things made up that cost to go? What was it made up of, cost to go? Tariff, very good. So, load, very good. So all the quantities, all the cost to go to the next state, right? To go to the next state from which there is an optimal path, right? So it consisted of two things: optimal cost from the next step and the optimal cost of all the actions. So it consists of two things: cost maximum over all action plus Vk plus 1. Vk, if you say cost, consisted of two things. So cost from cost over all A. So this will take you to Vk plus 1, and then the cost from there. Slightly in the slides you have got a full technical statement of that. So it consists of two things. I am at a place, I take an action, it cost me so much to reach the next place, right? And that place has cost to go, so I add that. Then every action takes me to a different place. I have got cost to go from that place, so I look at all the possible costs and pick up that action which minimizes my cost, right? So the two things, as you said, cost to go and action, but cost to go consists of two parts. One part is cost to the next level, next state, or next time step, cost to the next time step, and I minimize the sum of the two overall actions. Okay? So here the action is fixed because it's already optimal. Now, what was the difficulty we found with this? Where what we saw could be a problem, mathematically speaking, or practically speaking rather. The path to choose is आ गया ये तो एक बार लगा दिया टेबल तो wherever you start, you keep choosing that action and keep following. Okay, so you are identifying a slightly different problem in the sense that this process is done for a fixed tariff and fixed load and all that, and that might be, that's slightly different. But let's say tariff and load is fixed. We flagged it and we called it the curse of dimensionality. Right? Because here we had only 3 actions. In general, if you are controlling a DC motor, if you are controlling inverters, the number of duty cycles you can have is really infinite. You can break it down into 5 parts, 10 parts, but that will lead you to an unstable control most likely if you discretize it. Because your answer could be 0.0 or 0.12, and if you only have from 0.1 to 0.2, it will keep oscillating between the two. So there are many actions which are potentially infinite. So, and then potentially infinite means for each action, so even if you very, very finely you do that, for each action and for each state you have to go through this process, which becomes a bit complicated. So there are many solutions to that. What is the solution we looked at? We looked at a particular solution, or what did we think might be of help to us? Let me remind you. That's a good way to write. I wrote it slightly differently, but does not matter. What does this say to you? So if you read the literature, we should be familiar with the types of symbols and notations they use. So when somebody says this, what does it mean? What does A stand for? Action. What does S stand for? State. What does theta stand for? So what does this statement mean? Of, very good. Stable state. So why did you bring stable into it? Yeah, that's all right. So what does this line mean? This is a very standard notation. What does this line mean?
At that particular state.
Yeah, at that particular state, yes. Maybe you are saying the same thing, but can you say it in a technical way? With respect. This really means in all this literature, given S. S is given to you. Okay, this is a probability distribution, probability of event A given. So this is the standard notation, right? You will recognize. ये यूपीएससी का काम है, right? फटाक से. Probability of event A given that event B has happened, right? That's a very standard thing. So that's a standard notation. So given state A, S, this function outputs an action and parameterized by theta as they call. What I did was, and in my mind I simplify this whole process that we are using a neural network to implement it. Okay, if you look in the literature, they have got exponential functions and many things like that, because if you add up enough exponential functions, you can approximate any function, right? So there are many theories like that, and they are all very interesting and very, very fascinating theories. You might want to look at them, but for our practical purposes, we can understand that a neural network is doing that, where so this is a neural network. What I am trying to do is trying to help you understand the literature. If you read the literature, there are hundreds of websites where they've got help pages and there are so many people wanting to help you. But if you want to read the literature quickly, that's what I'm trying to communicate to you, that how would you able to pick up that literature quickly. Okay, so this is all clear? What we did. Now we go back. Right? Now we go back. So, how do you find theta? Pardon? Guess, very good. How do you find theta? Okay, guess the solution. Very good. Very good. I guess the solution then. Very good, sir. Very good. Okay, now how do I find the error? Very good. Beautiful. Everything in the world is done this way. There is nothing in the world done any other way. Right? So I guess the solution, that means guess theta naught. Right? Some solution, I have guessed it, and I have got a function, I have got a neural network. Right? Now I find the error. How do I find the error? So I am training neural network. For each cell I will train one by one. Right? That's how you train neural network. You will train for each cell, you will train. So because that each cell has got a different state, I'll provide that state here, right? And then I'll get the action or the value to cost to go. There are many things to do, many ways to do. I can have the action or the cost to go. So normally what they do is they calculate this cost to go, right? And try to play with that. So your output of this, if you like, is also QSA. Right? So that's also output of the neural network. It could have actions as output and the cost to go. So this is normally cost to go. Right? So now tell me, how do I get the error?
Applying a condition for that one place to go and giving it a reward.
Yes. Suppose we had a table from yesterday. I think, yeah, that's a better way to start. Suppose I had the table from yesterday. Right? I had the table. What will you do then? Yeah, that's a good way to cover it. We have this table ready. I have got this neural network. I guess theta naught. I start from this cell. I feed that state. Right? And obviously the output will not be the cost to go as I have calculated before, right? Because we have got some number in our table, definite number, 30 point something or whatever, it's there. The network will not have that number. So what do you do? What do you do? Sir, did I see you before? आपको मैंने पहले देखा? तो अचानक आप कैसे आए? हैं? आप कर तो रहे, बहुत बड़ी खुशी की बात है, पर आज अचानक फ्राइडे को कैसे दर्शन दिया आपने? Pardon? लोखंड, ओके. लोखंडेश्वर का आदेश बहुत बड़ी चीज है. ओके, सो आई एम जस्ट जोकिंग. मैंने आपको देखा नहीं इसलिए आई एम जस्ट सरप्राइज. नाउ आई हैव गॉट दिस नंबर. I forget the number. If you can look in your notes, it could be 33.5 or something like that here. Output of the neural network, will I get a number or not? I'll get a number. Maybe I get a number 20. What do I do from there? Yes.
Without any condition, it will not interpret the results what you want. So I think condition is important first to get which to start.
Okay, I'll repeat the question. I want to, ये बहुत, see in teaching over the years and in learning, sorry, teaching की तो बात छोड़ ही दो, क्योंकि कौन किसको कितना पढ़ा सकता है ये जानना असंभव है, पर in learning over the years I have realized that the less you learn, the more powerful it is. But what you learn properly. तो मैं बहुत कम आपको चीजें पढ़ाई है मैंने 5 दिन में, पर जितनी पढ़ाई है बहुत सॉलिड है. Today you may realize or you may never realize, but I had to do my job. So everything I have told you is very, very powerful. All those ideas are very powerful, right? So yesterday we started with a powerful idea. We went some far, but it is good to revise because like every human being, we forget, we don't understand. Multiple revisions help us, right? वो सबके लिए. तो मैं, I want to re-emphasize the process we went through. तो आपने, you did this as a result of our repeated emphasis. You have now sort of trying to think that way, right? So let's go back. I have got a table. I want a neural network to duplicate the functionality of the table. Problem clear? A neural network to duplicate the functionality of the table. आपने कहा neural network को मैंने initialize कर दिया theta 0 से, some random vectors or whatever I had. Then you said find the error. Then I said the way I have, so the neural network is doing for me. So let me put star here to say optimal, right? Otherwise confusion हो जाएगा. Theta A S is giving me 20. मैंने neural network पे state लगाई, state 1 or whatever it is, you can call, we can have names for that. I got 20. And I know that I should get 33.5. Right? Because I have created that table myself. कल अपन ने बना है वो table, that is solid, rock solid. I'm just trying to convert that information from the table to a neural network. Okay, now this gives me an idea that I will do it myself now. Okay, but anyway, वो छोटा problem है, that will be a nice solid problem. Because most of the problems we do are too complicated to understand these things. But anyway, let's continue the process. I'll implement it and if time permits, or now, not now, but later I'll send it to you. So find the error. So in this our context, what is the error? Yeah? So what is the error? That's the error. कोई मुश्किल काम नहीं है. मैं सही कह रहा हूं? वो एरर आ गया. अब हम क्या करेंगे? थर्ड स्टेप. What is the third step we said? What do we do now? Improve the? Yes. Not improve आपने ठीक कहा. Correct? Minimize the error to do what? Improving accuracy. So I minimize the error, choose delta theta such that pi theta plus delta theta AS is less than or whatever the pi theta. Well, this I'm putting it very loosely, okay? What I'm trying to say is I want to find delta theta so that my error becomes less. Right? So I want to find delta theta so that my error becomes less. And I have put it deliberately in that form and suggested by our friend the 3 steps. That's what you should think all the time. Now we can fill in some details. So I want to find delta theta, and we know we are dealing with neural network, right? So to find delta theta, what is an algorithm we had a look at? We had a look at an algorithm to get delta theta. Taylor series is a theorem that led to what? What is the only way to reduce error? Huh? Steepest descent is the only way to reduce error. There is no other way. So we find the steepest descent with respect to what? With respect to, see, steepest descent, so what is varying? Steepest descent means that you vary this thing in this direction and you will move the fastest. So what is the thing that is varying here? Theta. Thank you very much. We have made a lot of progress. Very good. So theta is the thing we have to vary in the direction of the steepest descent. Right? And that method is very efficiently यार कैसे भूल गया, implemented, very efficiently implemented using one particular algorithm. Steepest descent is an idea. You can do it in many ways. But for neural network, there is one particular way which is very powerful. Which is that way? बहुत powerful है. For neural network, yeah? Back propagation. You use the back propagation method to update your thetas. And you got the script, everything you have got. Like Python भी है आपके पास, MATLAB script भी है implementing this in detail, but all those packages implement it like that. But you have got a detailed implementation with you, you can follow through. And a very, very powerful idea. So these 3 steps are clear now. Firstly, we get the table. I want to convert that table into a neural network. All that process is clear because that is repeatedly you have to think through this process. I have got a table. I want to duplicate it using a neural network. And to do that, I follow these 3 steps. I guess the initial weights, put the known input. I have got a known output. If there is an error, I use that error to change theta so that my error reduces. So I keep doing. I keep doing all circulating. Maybe do it 100 times, 200 times, 300 times. And the experience shows that the neural network will duplicate the table. When you will give this input, it will get that output if you trained it enough number of times. Is the process clear? ओके अब इतना ही होता तो इसकी कीर्ति इतनी नहीं होती न्यूरल नेटवर्क्स की और इसकी लर्निंग की, सॉरी आई एम वेरी सॉरी, लर्निंग की कीर्ति इतनी जबरदस्त नहीं होती इफ दिस वाज ऑल, बट दिस इज द एसेंशियल, द हार्ट ऑफ इट. इफ यू डोंट अंडरस्टैंड इट, जो इसकी कीर्ति है वो भी आप नहीं समझ पाओगे. ये तो समझ में आ गया ना, टू डुप्लीकेट अ टेबल विथ अ न्यूरल नेटवर्क, एंड न्यूरल नेटवर्क इज कंटिन्यूस. टेबल में तो आपको डिस्क्रीट है, neural network is continuous. आप उसको यहां कोई भी नंबर देंगे वो आउटपुट देगा. तो कर्स ऑफ डायमेंशनैलिटी, दैट्स आवर होप to overcome the curse of dimensionality using neural networks. So this is very good, wonderful, but the power of this whole reinforcement learning is when I don't know the table. In general, I do not know the table. कल का अपना प्रॉब्लम सिंपल था. We populated the table, but in general, I will not know the table. Right? In general, I will not know the table. Is that are you convinced, or even 10% convinced, or 20% convinced that there will be situations where I will not know the table? Right? If there are, it's only had one state and 3 actions. If it had 5 states and 10 actions, it will be almost impossible to create that table. So there will be situations I will not know the table. So that's the first thing you have to convince yourself. इसको बहुत ध्यान से देखें, बहुत समझे इसका अर्थ क्या है, इसका तात्पर्य क्या है, कि सब इस पे, दैट्स द फल्क्रम ऑन विच दिस एंटायर reinforcement learning rests. I do not know the table. And so here why did we need to know the table in this process here? In this process we underwent before, what is it we picked up from the table? Why did we need to know the table to go through those 3 steps? What is in those 3 steps that depended on us having the table? Pardon? अरे आसान क्वेश्चन है, मुश्किल नहीं है. या अरे वेट्स तो अपन नहीं थे ना, वेट्स तो अपन आर्बिट्ररी स्टार्ट कर रहे थे. टेबल डिड नॉट गिव. यस, कॉस्ट टू गो, ये टेबल के बगैर नहीं मिलता ना. If I did not have a table, I would not have got that. So that crucial part of getting the error was dependent on me completely working out the table before. And if that was the case, that it's a big deal that information like that can be captured in a neural network. That is itself is a significant thing. I'm not saying that that's not significant. That we have got a mathematical structure which can capture complicated things. It is quite a remarkable thing. But much more remarkable is when I don't have this table and I can create a neural network to represent this table. What it would have been the right table. Had I been able to create the table right, then my neural network would duplicate the table. Right? This is not a small thing. So how would we do that? So that's the whole. People at Google and all who earn big money, they earn big money to tell us how to recreate this table or how to recreate the neural network without any initial information. Minimal initial information. So, I mean, मैं तो नहीं जानता सब, but even of people who know, they don't know everything, but there are many different ways, and each of these ways is to start randomly. ये सारा table, the same way as we assign theta not randomly, they assign this entire table randomly. Okay, and then they use that value, cost function, whatever is there as the actual one and update it. The 33.5 to start will also be a random number here. Okay, they use that, they kept doing for 1,000 times, 10,000 times, 1 billion times, and finally they converge to the value that you would have got had you done it all using a table. That is a very fascinating aspect of it. If you हर चीज का एक सिद्धांत होता है. You can work in neural network, there is nothing, there are all the libraries available. But if you want to do effective work, you have to understand how this randomness to start with gets converted to a definite information, which is used practically, which is of great advantage to us, which is a solution to very difficult problems. So we don't have time to go through all the scripts are there. I have given you the scripts, or you will be given the scripts which go through this process, right? So we don't have time here to go through, and that's all very abstract. Unless you do it with numbers, all these things are very abstract. And you have to have some patience to be able to interpret these symbols and methodologies and all that sort of stuff, right? So the script is there. So if you want to do the great things, plan this, plan that, plan battery, energy saving, optimal this, optimal that, and if you want to use machine learning, this is where you have to start with. I mean, you can do everything, you can get a PhD thesis, right? आपको रोक नहीं सकता without understanding anything. But if you want to sort of do a good thesis, good research in this, using this tool, okay? Very carefully I have used my words. If you want to have an application of machine learning for your application, if you want to apply machine learning for your application, where you understand the application very well, and you are using machine learning. So for good research, you should also understand that how starting from totally random information, you can end up with something which is so definite, so useful, so powerful. Okay, that's an essential thing you should do. You do it or you don't do it, I can't say. There are thousands of people who get a PhD without doing this. And you will get a PhD, there is no doubt about it. Spend enough time, you will get a PhD. But this is, to my mind, non-negotiable. Okay, so if you want working in that area, you have to figure out, this is the process we saw with definite information, and this process will converge very fast. We go maybe 100 times and it will converge. But starting from there, it might take 1,000,000 iterations, but still even million, I mean, it is fascinating why it will converge. So I would strongly recommend that people who do research in this area think about those things, and these are the steps. So the essential things are captured here. So whenever you look at an algorithm, look at these three things, that how are they doing these three things. So you'll understand it much faster. And the final step is, how do you get the desired value to get the error? To start with, in practical problems, we get the desired value as random numbers, and we keep improving from there and come to our answer. So it is quite fascinating. I mean, if you have got some curiosity, you cannot be but amazed at entirely a random operation can lead to such extraordinary result. And it is done through rewards and all that. It is not completely random. So you assign some rewards. You don't know the system, but you know under which conditions you need to award rewards, and one of them is if you are doing battery scheduling, then reducing the overall cost you pay to the utility company. So you know how to reward the algorithm. Okay, using those rewards, it will convert the random information to something very powerful, very specific in the form of a neural network, which you can use to do these tasks repeatedly. Okay, so this is what I want you to take from our discussions. Any questions? So now we switch gear, as they say.
Dynamic programming is computationally intensive.
Yes. Memory and memory more intensive in terms of memory.
Recursive.
Because calculations you need to do are very simple. But it's where you have to store all that information. So you have to store all the information to the right. You can't throw anything away. And then you come to the left. So it is a memory problem. So neural network solves that problem. Now we go a bit to a different direction. And we go back to something we did on day one. We go back to what we did on day one. When a system becomes unstable, power system, you would have, I think there have been many times grids have collapsed in India. So that's India is slightly different. Because most of the times grid collapse in India is due to what?
Overdraw. It happened, it don't.
Voltage variation, yes?
Overdraw of power.
Overdraw of power. So in India, what happens is you have got different grid zones, right? North, south, east, or सबका limit है. Okay, they can draw only this much. There are regulations. और रेगुलेशन वाले भाई कहाँ हैं? थे तो सही सुबह. ओके ओके. फोटो खिंचा कर चले गए. Okay, no, I'm just joking. So there are limits on tie lines what you can draw power. But I know that people regularly cheat. All the states regularly cheat. They draw more power than they are entitled to. तो उसके लड़ाई झगड़े होते हैं, that's a separate story. But unfortunately in India, that is the major cause of this interconnection gets tripped. Because when you are drawing more power, they just open the thing. And then it is north grid collapse, ki western collapse ho gaya. So that is one reason. What is another reason for instability in power systems? For which you got, I don't know how many of you are power system people, but AVR, PSS. So they are all devices installed to avoid instability. So how is instability done? Or how is, okay, let's put the question in different way. What do we regulate? Yeah, that might be a better question. So the central authority, you've got several central authorities. What is it they regulate? What do they want within that it should, this thing should be this thing should be that? What are the two key things? Well, I shouldn't say two. What are the key things they monitor or regulate? Voltage, current, frequency. Voltage, current, frequency. Anything else? Anything else? वो तो दूसरा लेवल है वो. Yes? Anybody else? Node angle and power angle. Anything else? इसमें नहीं आया? आ गया. Pardon? Load flow. So I agree that these are all things we have to continuously monitor. Right? So within this, can you identify the minimum set of parameters? These are all should be monitored. I have no doubt there. But can voltage and frequency. Very good. So what you are saying is that if I monitor voltage and frequency, I don't have to monitor those other things. Why would it be so?
Frequency directly is the function of load, which is by default will take care of current also.
So what you are saying is that frequency takes care of this thing, right? That's what you are saying. So if I monitor frequency, I don't have to monitor load flow. Okay? What else does frequency take care of? Okay, so voltage, what does voltage take care of? Because we have to cross everything else. If we are monitoring only two things, we have to cross everything else. Can we cross it? Impedance, आप जो कह रहे हैं, but they are not, I can't operationally monitor them. You can monitor them if you like, but operationally what is important?
So voltage will take care of load flow.
तो वो तो चलो दोनों लगा दिए, पर लोड फ्लो ही अपन ने नॉक ऑफ किया ना अभी तक तो. Okay, can you tell me why?
Because mainly load variation etc. may vary the reactance of the parameter.
Reactance तो fixed है, parameter. Yeah, I know what you mean. पर आप technically सही बोले. I know what you mean, 100%. What you are saying, I understand, and that's right.
Need of capacitance.
Yes? Reactive power? Not minimize, maximize का नहीं, वो किसका relationship अपन ढूंढ रहे हैं अभी? Very good, very good. So voltage, an indicator This is what you meant? Yes. Thank you very much. आपने भी roughly you meant that, I know that. So I have knocked power factor. Do I need current? If I know the nodal voltages, currents are known, right? What about load angle, power angle? Because it's a part of load flow, right? So they broadly come under the heading of load flow, right? So I need to monitor only two things, voltage and frequency. If I do that, I am monitoring the health of the power system. And as Madam said, that if I change the reactive power devices in the network, reactive load in my power system, voltage variations will show. And if I go back to my, so what do I do? Suppose my voltage is 1 per unit, it has gone to 0.99 per unit, right? So what is happening to reactive power? So what is, if I have 0.99, my voltage should be 1 per unit. It has gone down to 0.99 per unit. Why it has happened that way? Reactive power consumption is more. So how does 0.99 help it? Because of the? Yeah, so at 1 per unit I am there, somebody switched on a large inductor, the reactive power consumption is higher than I am generating. So how does 0.9 help the situation? आपने सब कहा वो ठीक है, पर मैं ये जानना चाह रहा हूं कि 0.99 how does it help the situation? Am I asking question? समझ में आ गया ना? How is 0.99 or 0.9 or 1.02 or 1.03 helping me with the situation? Well, our assumption is that reactive power consumption is a function of squared voltage. Right? In the transmission lines and all, the reactive power, if you do the equations, you will see that square of the voltage will be involved in reactive power consumptions across the transmission lines and all that. So our assumption is that most of the transmission lines are inductive. So if I reduce the voltage here, my transmission line reactive power consumption will decrease, and the previous whatever I am generating will be enough for the new load which has come and the transmission line. So it will redistribute the reactive power consumption of the network to come to a new voltage level. Okay? So that's how 0.9. So now I know that that's not the right thing to do. If I let it slide like that, so they let it slide like that, 0.99 they don't care, 0.98 they don't care, but then they suddenly wake up, because nothing, what can happen? Usme kya ho jayega? Right? The load is being supplied, everything is working all right. If instead of 240 volts here, 220 comes, kya hoga? Kuch nahi hoga. Not much trouble. But then they know that their generation is not matching the demand. So then they fix to go back to 1. They go back to 1 using AVR, and that AVR going up means that the generator is generating more reactive power. Right? And then the balance is there so that you know you are doing the right thing. So suddenly when you are at 0.9897 and if you don't make a correction, then suddenly the change might be too large for you to go back to 1. Okay, you might have voltage instability. So you keep correct. So voltage is not such a big crime. Uska, I think our regulation man is not here, but 10% is still, I think, the regulation, right? वोल्टेज का 10% रेगुलेशन है ना, ये फ्रॉम मीन वैल्यू और फ्रॉम द स्टैंडर्ड वैल्यू यू कैन गो 10% और 5% अप एंड डाउन। वोल्टेज का काफी बड़ा रेंज है, बिकॉज क्या हो जाएगा, कुछ नहीं होता। ओके, दैट पॉइंट इज वेरी इंपॉर्टेंट, यू टू रिमेंबर दैट पॉइंट। नाउ फ्रीक्वेंसी, why does frequency change? लोड एक, मैं भी एक शब्द में बोलता रहा तो आपको कैसी आपकी वो होगी हालत। लोड चेंजेस, active power, so the active power changes, right? So that's the first step. What is the second step? Active power changes, correct, I agree. Active power changes, पहला कदम। दूसरा, क्या फिर फ्रीक्वेंसी कैसे बदलती है? ये तो बच्चे होते हैं, वो ऑस्ट्रेलिया वगैरह में बच्चों से पूछो तो बिकॉज, वो स्टैंडर्ड जवाब है उसका, क्यों किया ये, बिकॉज, और फिर रुक जाएगा, जवाब कभी नहीं देगा। ये पता नहीं इंडिया में भी आजकल ये होता आई डोंट नो, पर हमारे जब बच्चे छोटे थे यही करते थे, बिकॉज। तो उसने कहा बिकॉज कहा तो यू हैव टू एक्सेप्ट कि देयर इज अ रीजन विदाउट देम टेलिंग अस द रीजन, बिकॉज। तो ये आप वो बिकॉज वाली बात कर रहे हैं, बिकॉज नहीं। लोड बदला तो फ्रीक्वेंसी क्यों बदलेगी? स्पीड क्यों बदलेगी? किसकी स्पीड बदल रही है? मेरी कार की, आपकी कार की, या जनरेटर, सिंक्रोनस जनरेटर की, राइट? द स्पीड ऑफ द सिंक्रोनस जनरेटर्स विल चेंज व्हेन द लोड चेंजेस, द स्पीड ऑफ द सिंक्रोनस जनरेटर्स चेंज। व्हाई डज इट चेंज? या इनर्शिया, सब वो पूरा वाक्य बोल दे, मजा आ जाएगा यार। अब 5 दिन में इतनी आपने झेला है तो थोड़ा और।
Falling back of the rotor, falling back of rotor in reference to the synchronous motion.
The falling back of the rotor, inertia, all your responses are right. So you are, let's look at load change की जगह आपकी बात मानी, load increases, अपन एक ही दिशा में करें, विपरीत दिशा में उसका उल्टा हो जाएगा, स्पीड विल चेंज। क्यों, मैं वो पूछ रहा हूं। यस, सो लोड चेंज हुआ, ओके, थैंक यू वेरी मच। सो लोड चेंज हुआ, सो व्हाई शुड द सिंक्रोनस generator electrical power change?
Supply the load. Supply the demand.
But what is it about synchronous machine that it will, उसने चेंज किया, आपने उससे पूछा तो नहीं ना, और आपने चेंज कर दिया, तो उस सिंक्रोनस मशीन में क्या है? ये थोड़ा सा डिफिकल्ट प्रश्न है ये, इज क्वाइट ए डिफिकल्ट क्वेश्चन टू आंसर, but you should think about it, that why does synchronous machine change its electrical output as soon as the load changes? जैसे आपकी कार है, करेक्ट, विंड आई सामने से, your speed will go down unless you press the accelerator, the speed will not. और यहां आप कह रहे हैं कि ऑटोमेटिक सिंक्रोनस जनरेटर नया लोड सप्लाई करना शुरू कर देगा। That's what you are saying, right?
Load draws the power whichever available there from the.
But the synchronous machine has to generate in the right way. ये ऐसा थोड़ी उठाकर चल दिए। That's a slightly complicated question that depends on the, वो सबको आपको जो भी उसमें कर रहे हैं कभी काम, you have to understand it. That the way synchronous machine is made, the whole structure, so it's like an outlet here. यहां आपने 2 एम्पियर का लोड लगाया, 5 का लगाया, 10 का लगाया, will it supply or not? Right? So it has to do with the properties of synchronous machine as a constant voltage device. So वो सब थोड़ा complicated है, but and you should know it. If you are working in that area, you should know it 100%. Even if you are working in the power company, you should know it. So synchronous machine, the characteristics of synchronous machine is as soon as the load changes, it supplies that load, doesn't ask any questions, right? But then continue your story. Yeah, then?
From the energy stored in its rotating mass.
Okay, so उसके पहले आपने एक step पहले कही थी. Yeah, mechanical. So what happens to mechanical energy input?
Mechanical input doesn't change.
Very good. Mechanical input does not change. So where is the difference going to come? उसने तो output करना शुरू कर दिया. वो तो उसका property पे आधार रखता है. उसने उसका output करना शुरू कर दिया. Input बदला नहीं है. So how would it be matched? It is matched by the change in the kinetic energy of the generator. It will either slow down or speed up. Yeah, decrease. So वो process clear है. And when that happens, the frequency changes. Why? Because frequency is proportional to the rotational speed. उससे क्या मुसीबत हो गई? बदल गई? बोले क्या मुसीबत हो गई? 50.1 कोई मुसीबत मेरे को तो नहीं लग रही. ट्रांजिएंट गए, खत्म हो गए. लेट्स से कौन से बताओ मेरे को. आज के पहले घड़ियां होती थी, अब तो घड़ियां भी नहीं है. आप बता दें कोई सा भी डिवाइस काम करता हो उस पर. यार 50 और 50.1 पे फर्क पड़ेगा क्या मालिक? 50 का आप 60 पे भी लगा दो चल जाएगा. ट्रांसफॉर्मर क्या फर्क पड़ेगा? हाउ मच सर? कोई 50-51 में क्या फर्क पड़ जाएगा? सो यू ऑल शुड डू दिस एनालिसिस. कभी जिंदगी में करना चाहिए कि फ्रीक्वेंसी 51 हो गई तो कितने लॉसेस बदलेंगे, क्या फर्क पड़ेगा? अरे कितने बदलेंगे यार? 50 से 50.1 में कितना बदलेगा? उसके लिए इतनी झंझट, दुनिया उसमें हजारों लोग लगे हुए दिन रात. I mean, these are very fundamental questions you should know inside out. I mean, you should not accept that frequency. आपने जो कहा सब लोग वो एक्सेप्ट कर लेते हैं. अब मेरे को बताओ तो सही वो सही है कि गलत है. पर वो एकदम एक फेमस एग्जांपल मैं देता हूं कि भारत में ये बहुत बड़ी मान्यता थी कि स्वामी विवेकानंद ने 0 पे 48 घंटे लेक्चर दिया यूएनओ में और उसमें शिकागो में. हम जब छोटे थे, अब आप लोगों का तो पता नहीं, हम जब आपने सुना कि सुना अब आप विचार करो यार, कोई आदमी 48 घंटे कैसे बोलेगा? और वो स्वामी विवेकानंद इतने महान थे कि लोगों ने मान लिया 48 घंटे बोलेंगे. मेरा कहने का मतलब यह है कि कुछ ऐसी बातें होती हैं which are easy to believe, they sound right. What you said sounds so believable that we all accept it. और एक बार वो एक्सेप्ट कर लिया तो आप गए, आपको हैंडल कभी नहीं आएगा. टेल मी व्हाट हैपन्स व्हेन दिस हैपन्स. वी हैव टू नो, क्योंकि नेक्स्ट जो मैं बताने जा रहा हूं उसका सारा आधार इन चीजों पे. वेल, आई एम ओनली हियर टू गिव यू प्रॉब्लम्स. राइट, ये रिचर्ड बेलमैन, मैंने इनकी किताब पढ़ी थी, तो ये कहते थे कि जब आपके भी डिपार्टमेंट होता होगा, पीएचडी स्टूडेंट वगैरह सब इकट्ठे होते होंगे स्टाफ के साथ, तो जब भी प्रोग्राम होता था तो पीएचडी स्टूडेंट से पूछते थे, भाई आपकी प्रॉब्लम क्या है, किस प्रॉब्लम पे काम कर रहे हो? तो साहब ये प्रॉब्लम है ये. तो उन्होंने कहा जब ये सॉल्व हो जाएगी तो क्या होगा? तो सब एकदम चुप हो जाते थे. ये नवीन समस्या नहीं है, बहुत पुरानी, मैं जब जन्मा था तब की बात है. और वो अमेरिका की टॉप यूनिवर्सिटीज की बात है। तो उन्होंने कहा था भाई आपका काम प्रॉब्लम सॉल्व करना नहीं, आपका काम प्रॉब्लम बनाना है, ऐसी प्रॉब्लम बनाए जो सॉल्व की जा सकती है, राइट। सॉल्यूशन के तो कई तरीके हैं, पर अगर प्रॉब्लम को ढंग से समझ लिया जाए एक बार उसके एकदम फंडामेंटल से, तो सॉल्यूशन आएगा, वो भी काम का होगा, आपको भी आनंद आएगा, राइट। सो and that's a very significant issue. I mean, all of you who are designing this converters and inverters and all that, eventually you have to connect it to the network, right? आपको connect करना पड़ेगा ना network में कभी तो. When you connect it, you have to worry about the stability issues. Then why does instability arise? ये मैंने जो शुरू किया. Right? So we have to see why instability. So what is, again we come back to the same stupid question. फ्रीक्वेंसी नहीं ठीक हुई तो क्या हो जाएगा? जितने कारण आपने दिए हैं वो मेरे को मान्य नहीं लगते। कल को आप मेरे को बता सकते हैं, आप लिया है मेरे मुंह पे फेंकें कि साला 50.1 हो जाएगा तो एडी करंट लॉस इतना बढ़ जाएगा, तुमको ये भी नहीं मालूम था, दैट इज पॉसिबल, पर अभी मैं उसको नहीं समझ सकता। See, so I have whatever little I have thought, maybe you have thought more, so you know that 50.1 the eddy current losses will be, then you the simple logic, मतलब इन सब की एक बहुत साधारण लॉजिक है। अपने यहाँ 50 हर्ट्ज है, यूरोप में कितना है? 60 हर्ट्ज, राइट। तो 50 से 60 हर्ट्ज में कोई अंतर नहीं पड़ता, ये तो सभी 50 रखते हैं या सभी 60 रखते हैं। Am I making sense? 10 हर्ट्ज का अंतर है भाई, कोई फर्क नहीं पड़ता, और आप 0.1 हर्ट्ज में परेशान हो रहे हो, राइट। सो व्हाट इज इट दैट गोज रॉन्ग, एंड दैट्स what my topic for today's thing is, to design inverter controllers for stability purposes. But first we have to know what causes instability. मैं सही तो कह रहा हूं ना? अगर फ्रीक्वेंसी बदलती है तो क्या होता है? किस तरह से आप समझेंगे? राइट और रॉन्ग तो बता दीजिए, तो आप क्लियरली नहीं बताया आप क्या कह रहे हैं। मतलब आपने ऐसा कहा कि दुनिया में आइंस्टाइन भी नहीं कह सकता आप राइट है कि रॉन्ग है। आप क्लियरली बताएं क्या कहना चाह रहे हैं। पार्डन? यस, तो उससे क्या फर्क पड़ गया? क्यों? ओह वेरी गुड, क्यों अनस्टेबल होगा?
सिंक नहीं होगा, मतलब ऑल जनरेटर्स आर कनेक्टेड टू द ग्रिड, तो वो जब स्पीड के साथ चेंज करेंगे तो वो सिंक नहीं कर पाएगा क्योंकि टाइम लेगा।
Very good, very good. They will not be able to sync. Now tell why it will not be able to sync. Very good. So the question is not 50 or 50.1, because why are they syncing at 50? बताएं।
जनरेटर्स उस पैटर्न में डिजाइन किए रहते हैं ना।
Not generators. आपकी बात, हाँ, not design. ग्रिड की बात छोड़ें, ग्रिड तो 60 में भी चलेगा, सेम ग्रिड में 60 के जनरेटर लाकर लगा दूं और चलाकर बता दूं तो ग्रिड सेम, इंडिया का ग्रिड और यूरोप का ग्रिड में अंतर थोड़ी है। आपकी बात 100% सही है, पर उसको जरा डिटेल में बताएं। Why would they sync at 50 and not 50.1? ये मेरा प्रश्न है। But why would it not do it at 50? क्या 50 में क्या मैजिक है? इंस्टेबिलिटी क्यों हुई? मैडम ने सही बात करी 100%, वो आई ग्रांटेड, पर आप उनसे ले, उन्होंने ऑलरेडी कह दिया कि सिंक्रोनाइजेशन विल नॉट बी देयर और सिंक्रोनाइज दे विल नॉट सिंक्रोनाइज बिकॉज दे आर गोइंग एट अ डिफरेंट स्पीड, राइट? आपने यही कहा ना। सो 50 पे क्यों वो सिंक्रोनाइज है? 50 पे इसलिए सिंक्रोनाइज है कि दुनिया को एडवर्टाइज किया गया है कि 50 पे आपको चलाना है। इज दैट राइट? हर जनरेटर वाले को बताया गया है कि अगर 60 का होता तो 60 का, 51 का होता तो 50, आप चाहे जो नंबर जो उसको दे सकते थे, पर ऑल शुड हैव गॉट द सेम इंफॉर्मेशन which is 50 hertz, they have got it. So there is no magic about 50 hertz or 51 hertz or 52 hertz. The magic is only having told them beforehand कि आपको 50 hertz पे चलाना है, वो उस पे चलाएगा। गवर्नर है, स्पीड रेगुलेटर चलाएगा। जैसे ही स्पीड बदली, राइट, तो आप मेरे को बताएं सब जनरेटर्स की स्पीड एक सी बदलेगी? नहीं बदलेगी, राइट? सो देयर रोटर्स will be moving with respect to each other, and then they will be exchanging power amongst themselves. तो जो रोटर आगे होगा वो वहां पावर डंप करेगा, और फिर जो रोटर स्लो जा रहा होगा उसको वो स्पीड करेगा, ये स्लो होगा वो स्पीड होगा, and then the exchange, so the generators will be exchanging power amongst each other rather than supplying the load. Right? आपका बात का ये conclusion, what you suggested, they will not be able to sync because normally if they are synced, the field of the two generators have got a fixed angle. आप उसके रोटर को मार्क करें, एक जनरेटर के दूसरे जनरेटर को रोटर को मार्क करें, and they will have a fixed angle. Right? दो रोटर फिक्स्ड एंगल पे चलेंगे, जैसे ही स्पीड बदली वो एंगल बदलता रहेगा, and due to that there will be exchange of power, and one will speed up and one will slow down. So 50 hertz is not an issue. What is an issue is that if it is not 50 hertz, we don't know what is other generator, because उसको थोड़ी मालूम है कि आप 50.1 पे चले गए, unless you have got a way of communicating. ये भी एक बहुत बड़ी बात है। आप पैरेलल इसमें इन्वर्टर्स you have, so there are schemes where you tell others you have changed your frequency, and that's power sharing and all that. So these are very important concepts. So unless you communicate कि मैं 50.1 पे चला गया हूँ, आप सब 50.1 पे आ जाएं, there is no way you will have a synchronized thing. Anyway, so it's very normal, by the way. In all, आप यहाँ लगाकर measure कर लें, you will never measure 50, because जो बड़ा generator होता है, which is power station, which is 3000 megawatts or plus there, they pull everybody. जैसे ये जनरेटर है that is dumping energy on this big guy, वो उसको तो कोई अंतर नहीं पड़ेगा, that will take it, and this guy will slow down on its own and lock in with the big generator. So normally frequency is not 50, it is 50, बदलती रहती है, and they have got an integral error which they put to 0. So we have come to two conclusions, and these are very essential ideas about power system. One is we monitor voltage and frequency. Now can you tell me in very nice complete sentences, Marathi में तो मराठी में, गुजराती में गुजराती में, हिंदी में हिंदी में, what is the importance of monitoring voltage and frequency? नहीं यार, अप्लायंस की वजह से नहीं, अप्लायंस का कोई फर्क नहीं पड़ता। हाँ, स्टैंडर्ड्स हैं, पर उसको क्या हो जाएगा, इसको 240 के 260 है, कुछ नहीं होगा, बिलीव मी। So, but we don't monitor because of that. That is the very vital, fundamental fact we should realize. That monitoring is not because of appliances, it is for a different reason. वही मैं कहने का प्रयास कर रहा हूं. And it's very easy to believe. जब लोग बाग आपको कहते हैं कि because of appliances you monitor voltage, it's very easy to believe. But that's not the fact. आप व्हेन आई टेक माई लैपटॉप, यहाँ नहीं है, पर आप ये लैपटॉप ले जाएं अमेरिका में प्लग कर लें, और अमेरिका का लैपटॉप यहाँ ले आए 220 में प्लग कर लें, कुछ नहीं होगा। आपका यहाँ तो वोल्टेज वेरी करता रहता है खूब, कुछ नहीं होता। योर लाइट्स आर देयर, एवरीथिंग इज देयर। सो व्हाई डू वी मॉनिटर? वो अपने डिस्कस कर चुके। सो आई वांट समबडी टू समराइज इट फॉर मी। वो चीजें इतनी ब्लैंकेट स्टेटमेंट है ना, अब उसमें कोई कुछ कह नहीं सकता और कोई कुछ समझ नहीं सकता। आपकी बात सही है। एक्टिव पावर फ्लो, दैट्स समथिंग डेफिनेट स्टेटमेंट। देखो अपन ने क्या प्रोसेस किया था, ये सब लिखे थे, एंड देन वी क्रॉस्ड आउट अ फ्यू थिंग्स रिलेटिंग इट टू जस्ट टू थिंग्स, राइट? तो वही प्रोसेस आप रिविजिट कर लें। ओके, सो एक चीज एक बार, बाय मॉनिटरिंग वोल्टेज व्हाट कैन यू एंश्योर? रिएक्टिव पावर। पूरा सेंटेंस बना देते, मेरी भी तबीयत खुश हो जाती है यार, हैं? बाय मॉनिटरिंग वोल्टेज वी कैन make sure that there is a reactive power balance between generation and load. Everybody agrees to that? By monitoring voltage, I make sure that I am generating enough reactive power to supply the load, right? Pardon?
Supply and generation
Of reactive power. What about the frequency? यार आप सेंटेंस बोल दो ना यार मालिक, क्या पूरा सेंटेंस बोलो।
By monitoring frequency, we can ensure the balance between load and generation of active power.
वेरी गुड, थैंक यू वेरी मच सर। राइट, बहुत साधारण चीजें दोनों, बट वाइटल। नाउ अब इतना ही होता तो बात क्या थी? What is the one major assumption between voltage and reactive power? बहुत इंपॉर्टेंट बात है वो।
ideal assumption.
मतलब there is an assumption we have to make to link voltage with reactive power.
Voltage variation does not affect the frequency or load current.
नहीं, वो तो फ्रीक्वेंसी तो नहीं करेगा, इट विल एक्सचेंज द पावर, बट देर इज अ ब्लैंकेट assumption, there is a very important, let me give it to you. कहाँ है? This is a very important assumption, right? Your transmission lines are mostly inductive, and if your transmission lines become resistive, this assumption is no more valid. Okay, so this if you break it down to load this angle delta, which you relate to the real power, then it all breaks down. If it is a resistive line, delta gets related to reactive power and voltage gets related to real power. ये बहुत बड़ा, you have to know this thing, very important. That if the transmission line is not inductive, that means you can ignore the resistance, which you can definitely ignore in high voltage lines, but you cannot ignore in, suppose the wires in this VNIT, you cannot make that assumption. So it's more complicated. Okay, so having come so far, let's, so मेरे को एक लेक्चर तो लगेगा। No, 2 to 3. That's all right. After 3, I'll. Okay, so maybe अपना टाइम हो गया पर लंच थोड़ा 2 मिनट कम कर लेंगे हैं. Yeah, so the problem I'm trying to tell you now is, I have got inverters, right? I don't have synchronous machine, let's say. I have got only inverters, I have got batteries, solar, wind, right? I am connecting parallel interconnection of inverters. So अपन problem अभी देख लें. आप lunch खाते खाते टाइम सोचे. So all जो अपन ने अभी चर्चा करी है, that is vital, and this took people a few years to come down to these conclusions. They did not have, of course, the facility of the computer simulation we have. They did all by hand and insights. But it formed a very strong basis for interconnected power systems. अगर ये नहीं concepts clear हो, so you cannot operate an interconnected power system. So you have to have crystal clear concepts what we discussed. And I don't think that you can not have these concepts crystal clear in your head if you are doing anything related to power systems. So how do we use this already digested understanding to parallel थोड़ी मुश्किल क्या है अपन समझ ले पहले. To operate an interconnected power system dominated by synchronous machines, what is it we monitored? How did we do? The डॉक्टर पल्स नापता है, वैसे अपन ने क्या नापा था? क्या नापते हैं? In the current situation, what are the things we monitor to make sure that the system is working properly? अभी क्या करते हैं? क्या? और क्या मॉनिटर करते हैं? यस? ये सामने बोर्ड पे है, अपन ने इतनी चर्चा करी, इसमें इतना परेशानी का क्या कारण है? वोल्टेज एंड फ्रीक्वेंसी. साधारण बात है ना, कोई इसमें ऐसा झंझट तो नहीं है. वोल्टेज एंड फ्रीक्वेंसी, राइट? What do we do for parallel connection of inverters? Can we just do this voltage and frequency? ये वोल्टेज एंड फ्रीक्वेंसी तो घुस के होना चाहिए. रात में कोई सुबह उठाकर पूछे वोल्टेज एंड फ्रीक्वेंसी निकलना चाहिए. इफ यू हैव एनीथिंग टू डू विद पावर सिस्टम, एंड व्हाई, वो इतना सॉलिड होना चाहिए कि देयर इज नोबडी कैन शेक दैट. बट दैट उसका सब चीज उस पर आधार है कि हाउ दिस पावर सिस्टम इज रन. इफ यू डोंट हैव एन फंडामेंटल अंडरस्टैंडिंग ऑफ दोस थिंग्स, यू कैनॉट ऑपरेट अ पावर सिस्टम, राइट? वोल्टेज एंड फ्रीक्वेंसी. अब अपने को नया स्मार्ट ग्रिड है, ये स्मार्ट क्लासरूम है, सब स्मार्ट हो रहे हैं अपन. तो उस स्मार्ट ग्रिड में अगर मैं वोल्टेज एंड फ्रीक्वेंसी मॉनिटर करूंगा तो मेरा काम चल जाएगा. क्यों? ये माइक्रोफोन मैडम को आप देकर रखें. हाँ बोले. यस, यहाँ यस, तो उसमें क्या, हाँ वो तो होगा, आई एग्री होगा. तो उसका व्हाट इज द कॉन्सिक्वेंस ऑफ दैट आप कह रहे हैं?
monitor that also for the same time.
नहीं आप ओके व्हाट सी कई बार क्या होता है कि यू आर टेलिंग द राइट थिंग बट इट मे नॉट बी रिलेटेड टू व्हाट वी आर डिस्कसिंग. व्हाट वी आर डिस्कसिंग इज what should we monitor in an interconnection, in a power system which is formed by parallel interconnection of inverters to make sure that the system is healthy.
Sir, I think we have to monitor currents also. It can form loop currents in parallel operations. So currents are also important.
Okay, ठीक है. अपन जैसे वहां शुरू किया था अपन कर सकते हैं. तो वोल्टेज फ्रीक्वेंसी में रहने दो कि काट दूं? रहने दो कि निकाल दूं? चाहिए सर. करंट कुछ और, पर प्रॉब्लम क्लियर है ना. हमको इंटरकनेक्टेड सिस्टम या ग्रिड आपको कोई दे दे, सबको जनरल मैनेजर बनना होता है, राइट? कौन दुनिया में ऐसा नहीं इसको नहीं बनना होता, पर आपको बना दे तो आप करोगे क्या? हैं? अगर कोई आपको बना दे तो करोगे क्या, पता तो होना चाहिए ना. और दुनिया में तकलीफ ये बहुत जनरल मैनेजर बन जाते हैं, इनको पता ही नहीं क्या करना. पर आई होप यू विल नॉट बी वन ऑफ देम. तो बताएं क्या हम मॉनिटर करेंगे? व्हाट इज इट वी विल मॉनिटर टू मेक? इज देयर द प्रॉब्लम सेम और डिफरेंट? हाउ हैज द प्रॉब्लम चेंज? और इट इज द सेम प्रॉब्लम. मैं फिर वो, क्योंकि मेरे को बोलने का शौक है, मैं बोलता जा रहा हूं. प्रॉब्लम बदली है या अपन वही के वही है? बदली है. क्यों बदली है? देखो, कोई भी नई चीज सीखो, और तो आपको मार पड़ेगी अगर आपने गलत आंसर दिया तो.
Voltage and current, they lead or lag, has a meaning.
Yes.
That's all.
आपकी
Intuitively, I am just saying.
नहीं, वो तो ठीक है कि इट डिपेंड्स ऑन द पावर फैक्टर ऑफ द लोड और व्हाट नॉट. पर अपनी समस्या ये है कि पावर सिस्टम बराबर चल रहा है या नहीं चल रहा, कोई तकलीफ आने वाली है या नहीं आने वाली है, इसका पता कैसे लगाना है. सिंपल. अभी अपन लगा रहे हैं, सिस्टम चल रहा है, फर्स्ट क्लास चल रहा है, राइट? जब से मैं नागपुर में आया हूं था, मेरे ख्याल से एक बार कुछ सर्किट ब्रेकर हुआ था, राइट? वो संडे को कभी हुआ था. हाँ, पावर एक बार. और उस गेस्ट हाउस में मेरे ख्याल से यूपीएस है, तो फटाक से आ गया. पर इन जनरल वी आर एबल टू रन दिस पावर सिस्टम. तो क्यों साला हेडेक करना यार? अगर इन्वर्टर लगा भी दिया तो क्या चल रहा है तो चलता रहेगा, कि वी हैव टू थिंक समथिंग डिफरेंट. यस, हार्मोनिक. पर उससे देखिए, आप ये सब चीजें वैलिड हैं, पर उससे स्टेबिलिटी में फर्क पड़ता है क्या? देयर इज अ प्राइमरी प्रॉब्लम, देयर आर सेकेंडरी प्रॉब्लम्स. Harmonic injection 100%, it's an issue. But does it affect it so much that that will be our primary problem? Here we are trying to look at our primary problem. That's the secondary problem, I agree. So you can do research, you can do a nice PhD on harmonics, and it is all a very genuine requirement. Okay? But what is the primary thing? फर्स्टली मेरे को पता है प्रॉब्लम. आपने कहा चलो आपकी बात मान ली, हार्मोनिक कंटेंट वो बदला है. हाउ एल्स हैज दिस थिंग चेंज्ड? तो चलो, इट्स अ गुड प्लेस टू स्टॉप. व्हेन वी कम बैक, आपको मेरे को बताना पड़ेगा. आप गूगल कर लें, चैट जीपीटी कर लें, जो भी कर लें. हाउ हैज द पावर सिस्टम स्टेबिलिटी प्रॉब्लम चेंज्ड और विल चेंज when we have got an interconnection, parallel interconnection of inverters as opposed to the parallel interconnection of synchronous machines. ठीक है, क्वेश्चन क्लियर है? फिर मत कहना कि साहब आपने यार ठीक से तो बोला ही नहीं था. हिंदी में भी कह दूं, मराठी में तो नहीं कह सकता. कोई गुजराती है या? नहीं, मराठी लोग मेरे से वैसे ही इतना गुस्सा रहता है. I won't insult their language. है? तो हिंदी में ये कि समस्या हमारा बहुत अच्छा मित्र है मराठी वो हमको कभी मानता नहीं है कुछ। अरे तुमको क्या पता। एनीवे, सो आप सोचें कि जो समस्या है पावर सिस्टम को सुचारू रूप से चलाने की, अभी की जो समस्या है और आने वाले ग्रिड की जो समस्या होगी वो एक ही है या भिन्न है, ये आपको बताना है व्हेन वी कम बैक, राइट। अब ऐसा मत करना भाग जाना, वर्षा मैम का बहुत इंटरेस्टिंग लेक्चर है, हैं, गायब मत हो जाना आप लोग। अपने वो सज्जन तो गायब ही हो गए यार, कहाँ बैठे? अरे सर आप तो 2 दिन से, अब तो वहां से गायब भाग के आप यहाँ गए, तो मैं पकड़ने वाला था, वहां आपके अच्छे मित्र हैं ये, मतलब क्या आपका, आई वांट टू अंडरस्टैंड, आप यहाँ आराम से बैठे थे राइट, अब वहां क्यों गए बता दो। प्रॉपर फ्रॉम, और उसका अच्छा आप बीमार थे, पर आप यहां से उठ के वहां क्यों गए? एसी, ओके एसी की वजह से, ओके, हर चीज का कारण होता है मेरे भाई। ओके ओके सर, सी यू आफ्टर लंच।
ఇప్పుడు గెస్ట్ హౌస్కి వచ్చేయండి ఇద్దరు.